Are you starting? Yeah. Are you? Yeah. We'll go over that. Oh. Perfect. Oh yeah. You should open it. Okay. All of you over here.
Oh, we're all lining up.
Yes, sir. That's great. Yeah. Okay. So, should I start?
Let's shoot the car.
Yeah. So this is the two-stage rocket mechanisms PDR presentation. So the mechanism system overview, we have three subsystems: the air brakes, which creates a controlled drag on the rocket. We have brand new this year, the retractable rail buttons, which will implement a passive retraction method after launch to reduce drag that rail buttons cause. And then we also create an avionics bay, which houses the electronics flight computer. It'll have some cameras, and it needs to be airtight from the air brakes themselves. This year, we have changed a little bit of how the systems are interfacing with the rocket itself. The plan is to create a bay that goes completely in between two couplings. The top plate and the bottom plate would attach each to a coupling. There would be rods through the center for structure. And then that center coupling would separate the avionics bay at the top from the air brakes at the bottom. So for our air brake system, we have Raj and Hayden. And I think, yeah.
For our air brakes, compared to last year, we have some design requirements that we do need. Here, where's that laser pointer? It does need to fit within the allotted space, obviously, that we've been given. Obviously, we can minimize that if we have extra, obviously, also that's good. But we're trying to improve and make more efficient the amount of space actually that we have extending past the sides of the rocket, giving us more than the 5¼ inch squared of extension outside of the rocket that we had last year. Obviously, the fins that do come out, we have a fin system. Obviously, the fins that do come outside of the rocket, they need to be flush at launch to reduce drag there. And when they do extend, we need to make sure that through their entire movement, they don't create a moment on the rocket, messing with the rest of the control systems, messing with like any of the guidance systems. Just go there. Earlier, we had a separate design that we had kind of played around with. It was based off these pedals that would rotate out of the rocket that were controlled from a gear mechanism on the inside. But we decided that it wasn't really feasible because the amount of, I would say, like the amount of area that we would get outside of the rocket would have been that 5.76 inch squared of surface area just outside, giving us leeway to put drag and control the rocket. But as a trade-off, it chunked out 60%, over 60% of the diameter of the rocket. And that's just going to mess with structure, the stability. And so from last year, that was pretty much a downgrade, and we couldn't see any justification to use it because last year we only had around 40% chunked out, and that really kept a lot more of the structure and strength of the tube. For this year, we came up with a flap design that's been seen before, but essentially we would cut out parts of the rocket tube and attach a mechanism from the inside to extend them kind of from flush to out, and that would let us control the drag that we would put on the rocket. It's controlled by a lead screw that's on the inside here that turns, and this plate moves up and down, bringing that linkage to extend and retract. Yeah.
So how this integrates with the proposed mechanisms bay is the actuation plate would use the structural rails as the way to prevent it from rotating, slide along those. But because we're proposing to have parts of the actual rocket tube fold out, that's why we have the structural rods and also why we have that coupling plate. We would have a tube. The rocket tube would go from this top plate all the way to this coupling, and then from here, the rocket tube would actually be attached to these flaps, and it would all fold out. How much of the rocket tube is folding out is up in the air. We need to do the calculations for that. So as right now, we have it modeled where it would be the entire rocket tube that folds out.
Yeah, so a lot of what we have created so far, we've used arbitrary numbers to figure out the dimensions and the sizes of everything. So our next step would be to do the hand calculations on the drag, the force, how far the angle would need to be of the flaps coming out of the rocket tube. Those calculations to get exact numbers on how the flaps would actually come out and what that would mean, like how much drag it would create in those aspects. We would also want to spec motor and the lead screw, make sure we're going to continue in the CAD with the motor and the lead screw to make sure that all the measurements are good and that everything is finalized so that it's working properly and that there isn't any sort of, we can troubleshoot any sort of issues that come up, whether that's with the motor or the lead screw or how they interact. We'd also do the same thing with the flap size. Like I said before, the dimensions for the flaps are pretty arbitrary at the moment in our CAD. So we'd want to finalize those sizes, which would connect with our calculations. Those go hand in hand to make sure that the size would be appropriate for us to achieve the necessary drag and other aspects we would need during launch. And then we'd hopefully prototype the rocket and test it out and potentially test it in a wind tunnel as well to see how our hand calculations and the sizes and functions of the mechanisms as a whole would, or the air brakes rather, would work out realistically. And that would help us also troubleshoot some of our calculations. And to finish off, we'd finalize the CAD, make sure all the numbers are in, make sure all the aspects are working nicely together. And yeah.
I'm in charge of the avionics bay. My name's Colin. So for the design requirements, we have to fit all the components from the electrical inside the coupling designated for the av bay. We include 2 cameras, one facing down similar to last year for the air brakes, and then one having an external view. We also need to mount the flight computer, the battery pack, external GPS, and then verify that it's airtight with the air brakes. So we don't have to worry about the antennas this year. Last year we mounted them. This year they're going to be wrapped around the outside of the rocket. We're going for a stack design similar to last year, and differently we're going to mount the battery pack in the av bay to help with wire management and giving the air brakes more space. So this is our CAD drawing for the side view of the entire av bay assembly. So you can see some measurements there. We have a designated, I think, 11 inches for the av bay on the rocket, and we're only using about 6 inches of the vertical space. The rods for the structural support right now are about 1/4 inch in diameter. That may change due to structural support with the air brakes. and everything is pretty much subject to change depending on EnP. So moving forward, we have to get the approval on the design, integrate it with EnP, adjust the dimensions. Then we are questioning where exactly to mount the battery pack, depending on weight and wire management, if it should be on the bottom of the coupling next to the air brakes versus on top. And we still have to CAD up and design a outward facing camera, hopefully to minimize drag. That's still up in the air, depending on where exactly we mount it. And then finally, do all the hand calculations for the forces and support and structural. That's pretty much it.
All right, next up, we have retractable rail buttons, which Ben and I are working on. As far as the design requirements go, we're making it to interface with a standard 15-15 launch rail. We want a retraction method that causes minimal friction during launch, and we want the button flush with the outer diameter of the rocket after launch. We want a passive retraction method, so we don't want to involve any like electronics or motors. So we came up with using springs. And then we want the retraction mechanism to occupy a small radius inside the rocket. So excuse me, the designs we came up with were the post designs, which is the one on the left. It utilizes a ring that attaches to the inside diameter of the rocket, then has two posts with springs connected that would pull the rail button back. We have the button design, which is the one in the center, which has a button guide, which is the top piece, which would connect to the rocket, and then the rail button itself with two tabs, where a spring would be between the rail guide and the button to allow it to retract. And then we'd have something at the back to stop it so it retracted to the right distance. And then last, we had a linkage design, which utilized two different links, one that wasn't free to rotate on a rail and another one that was free to rotate, and then a spring that would essentially like pull it back into the rocket. So the pros and cons of this design. For the post design, it was the largest by far. The ring around the whole rocket wasn't very practical, and we decided there weren't any major advantages to this one. The button design, it was the smallest. It only requires one spring, which makes it the least complex, and it also has the fewest number of parts. As far as the linkage design goes, it could potentially be the thinnest design because it'd be wider than it goes far into the rocket. However, that said, it's certainly the most complex with the two different linkages and the spring, and it has the most parts, which would also make it the hardest to manufacture, which made us believe it wouldn't be very practical to actually do.
So going over the button design, we have the button guide here, which has a radius on the outside to try and keep it as flush to the outer surface of the rocket as possible and reduce drag. There's some slots over here to guide the physical button to make sure it's always aligned with the rail. And then there's some screws here to attach the bottom plate, and then some outer screws here to try and come up with a way to mount it onto the rocket, which we're still tooling with that a little bit. And then for the button itself, this would be the most complicated part to design out of this system. And again, it's made to fit those 15-15 rails, and the fins here help to make sure it aligns properly. And it again has that radius to try and keep it as flush as possible. And then the bottom plate is just very simple, and it just helps keep the button from going too far into the rocket. So it's, again, as flush as possible, reducing as much drag. And then next steps would be hand calculations to calculate inspect the spring to figure out how strong the spring needs to be, what forces are involved to make sure our mounting mechanism will work correctly, and then hopefully do some prototyping and testing, and then finalize the CAD with that mounting mechanism. Any questions?
question about air brakes. I
Yeah.
understand you guys go about to make down the motor. Are there considerations of, well, the first two, no, the correlation between like, data change and how much you rotate with the screw and how much the box will out?
No, we would require the we need to calculate the force that would be pushing in on the flaps before we can spec the lead screw. So that's all planned to be done in the future. We have not looked into speccing the motor yet, but if we would probably, if that's required or wanted by EnP, we would look into that. Mhm.
Awesome.
Yeah.
On the like rail guys that pop in, how are you guys planning on like having them out for long? Like to set up on the rail?
Oh, so what we can do is use a magnet to pull them out and then place them on like a little 3D printed slot. And then if you slide the rocket onto the rail, the like 3D printed part would just pop up the top.
And then I guess the other thing is with those, it's obviously not gonna be a lot of force, but it will be pulling
Mhm.
against the rail.
Yeah,
Is that a concern at all, with the friction of that?
it could be, but we're going to ideally look into testing different springs and how the rocket would actually interact with different spring constants, different spring forces.
Exactly.
The air brakes and aft bay are located at the very bottom, right above where the motor is. It's where they were located last year. Oh, it's in the upper stage, so it's above that.
And 9. Has there been any consideration making sure that it can fit between the couplings? So it looks like it might be cheaper.
Yes. Well, I was looking at the couplings. It looks like they're one piece this year, and we wouldn't be sliding through them. Also, with this design, we would attach the top and the bottom plate directly to the couplings, so the rest of it wouldn't need to slide through. Uh-huh.
Oh. Yeah, yeah.
For the linkages on slide 8, do you have, I know Rohan kind of asked this question, do you have any idea like, what torques those could handle? Like, or have you spec any torques? for the
No,
linkages? Okay,
we have not at all.
okay, which, this is, like, people do this, so I'm sure it's not.
Yeah.
What percentage of the body tube is missing? I know you had actual percentages for the last year and another, so that you had any idea of this one,
So,
especially with it having to not be exactly flush with the acid.
yeah. So how it's modeled right now, there is no tube on that bottom section. We can look into adding like sections of the tube back, but it would be a considerable amount of the tube missing. That's what those rods in the middle are for.
So we're depending entirely for that section of the rocket on the rods.
Yeah,
What are the rods made of?
we have not looked into speccing that yet.
Kind of similar question. So if this is completely open, I would be a little concerned about like air pressure affecting the mechanisms. So you're saying it would almost look like how it does in the render, just kind of open.
Yeah,
Okay.
but there'd be Yeah, we imagine the rocket tube kind of just cut 4 ways, and then each of those 4 pieces would be attached to those flaps right now. So when it's folded together, it all comes together and it's one tube. Yeah. And then
You're saying, so there's not gonna be an inner tube.
Yeah.
There's no structural support, but from the tube, there's no structural support, but there's there for aerodynamics.
yes.
So you're like after there. If we realize after it's like extended,
So they're
that there's like
putting
inner tube,
cylinder
there's
stuff
nothing
to
pushing stuff.
That's an issue every year.
I get that. But like if we want to put something.
The air is pretty good, same, but it's open, there's no body tube that's supporting it.
Basically, it's bottom.
Yeah. And like all air brake designs, when you open them, air comes in, so.
Was to make it flush. I would reassess that and a couple of your other goals. Because you're not going to get any of these things 100%, so please look into getting some tolerance that determine how big the gas between the airplanes.
Yeah.
work and how flush it actually
Mhm.
is a bit more fun.
Next question was, for wind tunnel testing, it's probably a little too big to fit inside the test chamber, so how are you planning to test it?
We have not checked that yet, but we could just take one flap and just see how that interacts with the wind tunnel. Ideally, there'd be a cavity, but the size of it wouldn't, like, we'll have to look into that. Yeah.
There is a bigger one. The developer said. But I was gonna ask if you talked to him, but we're gonna do a meeting with him next week. I was already gonna ask about the wind tunnel for GNC, but I'll also ask about
Okay.
Eric's.
Yeah.
And see how they do.
Say, that's all for questions.
Mhm.
Well, we have some more questions, but we'll share them with you after.
Yeah.
Okay, thank you.
By the way, once again, any of the questions that didn't get asked, we do have that form and get them on the answer question.
Or just send us to one of us.
Yeah.
So for presentation.
I think it's.
Then you got picture first.
Oh, yeah.
It should run better.
Use the slides to the.
It should run better.
We have a large team, so maybe we gotta give a lot to each other.
That's.
Yeah, you can look at it. So they want. I guess we can start with that.
Hi, everyone. We are the two-stage rocket composite sub-team. My name is Alex Van Gelder.
Thanks, Tom.
I'm Meyer. I'm Cole.
I'm Noah. I'm Joel.
I'm Jay.
I'm Matthew.
And this is our preliminary design review.
So the two-stage rocket is broken up into two stages, the sustainer and the booster. The different sections that need to be built are the nose cone, upper airframe, the middle airframe, avionics airframe, the lower airframe, a transition tube between the two stages, and then a booster, body tube, upper airframe, and lower airframe. One key thing to note is that the sustainer has a diameter of 5.15 inches, and the booster has a larger diameter of 6 inches. So the fins, we'll be using very normal trapezoidal shape fins with beveled edges. Key thing to note is that the booster will have slightly larger fins, larger in height and in sweep angle, and larger in height and less in sweep angle. Our current timeline is that we are on pace with all of our plans for the year. Currently, for B term, we are planning on doing a lot of manufacturing work, doing practicing, as well as beginning material testing to determine material properties.
Okay, now to talk about some of the analysis work we're doing. So for an overview, we're performing finite element analysis on the fin can assembly using Abacus CAE. You might be wondering why we're not using Ansys, and the answer to that is because it has some struggles with interfacing between composite layers, which without proper interface can lead to possibility of composite failures. And obviously we don't want that when testing our or when analyzing everything we need to analyze. So some analyses we plan to run are thermal load tests, which will study how thermal energy affects the structure over time. Thermal stress analysis, which will study mechanical stresses that develop in the material due to temperature changes. Modal analysis, which are used to determine the natural frequencies and mode shapes of a structure, such as in fin flutter calculations. And dynamic analysis, which shows how a structure actually responds to real-world time-varying forces, such I did not mean to do that. Such as thrust buildup, launch pad vibrations, and stage separation. So building off of previous work from last year, they studied and analyzed fin phenomena such as fin flutter, and they manufactured and tested composite coupons. And different from what we're doing, they used Ansys to make structural and CFD simulations based of their fins based on experimental data that they got from their composite coupon tests. So for our progress in A term, we have built familiarity with Abacus. We used tutorials, began working on our FinCam model. We learned how to create partitions on imported models in Abacus. And what a partition is separations made between different parts, such as the fins and the body tube, to allow us to assign different material properties to get more accurate results with our finite element analysis. And these partitions are particularly important for assemblies that have a lot of parts or a bunch, such as the fins, fillets, and the body tube. We also researched testing procedures and obtained access to Materials Testing Lab to actually conduct those testing procedures. And we learned how to use the results of testing to calculate the required material properties.
So two different types of tests that we'll be conducting to determine the material properties will be a tensile test and a shear test. And we'll be conducting these tests using coupons made in the shape of dog bones. And this is so that we can center the center the forces into the center of the coupon to more accurately understand how the tensile stress affects the coupons. We will be fabricating between 3 to 5 specimens, and we'll be conducting these tests according to ASTM procedures. And we will be doing them on machines like what you can see in the slide, like in the Instron machine, which is a tensile testing machine. So based on these tests, we will be determining the different material properties, namely the modulus of elasticity in the 1, 2, and 3 fiber directions, the Poisson's ratio in the 1, 2, 1, 3, and 2, 3 planes, and the shear modulus in the 1, 2, and 3 axial directions. And if you are unfamiliar with the composite coordinate system, which I'm sure not everybody is familiar with, 1 refers to the direction that the fiber is running, 2 refers to the transverse direction, so going perpendicularly, and 3 refers to perpendicular but in the upward or downward direction. And the planes of 1, 2, 1, 3, and 2, 3 are combinations of those directions.
One of the major design challenges our composite team tackled this term was how to bevel fins, and more specifically, how to design a jig for making beveling fins easy and fast. The reason we bevel these fins, for those of you who don't know, a bevel is essentially a chamfer on the edge of the fin that makes it more aerodynamic by reducing drag. But we need to be careful to not bevel it too much, where it would create essentially a knife edge that would potentially damage the fin when it impacts the ground. Building from this, our design requirements that we were given were a 4-degree double bevel on both the leading edge and the trailing edge of the fin, and a 1 millimeter flat between the 2 bevel sides to avoid a knife edge that's both dangerous and potentially damaging for the fin. The first design we looked at was essentially a 3D printed ramp that mounts off of the belt sander, off of 2 locating holes in the bottom right, clamps there, screwed in through 1/4-20 bolts to the already existing holes on the sander, so pretty minimal setup time. Fully 3D printable in one piece, most likely out of PETG or similar filaments that are heat resistant, because one of the concerns we have, we'll address later, is that this sanding jig might heat up. And the sanding procedure is essentially the fin rests on the inclined plane and moves laterally along the direction of this upper red arrow. You flip over for each bevel and then rinse and repeat for the other side for both the leading and trailing edges. One important thing to note is that this sanding jig has a physical stop that prevents the fin from going in too far and taking off more material. So the sanding procedure is pretty straightforward for this. No need to do any weird measurements or markings. Should be butting it right up against the hard stop. So the pros are that this is fully 3D printable in one piece. It fits on the side. It's about 8.5 by 8.5. It'll fit in the bed of a P1S or similar size printer. It's got 0 moving parts, so minimal assembly time and mounting time. Fairly easy to sand the side of one bevel in one smooth motion, so no need to go in and out and potentially lead to uneven surfaces. And it locates off of pre-existing holes, so again, that makes it pretty consistent on the sander and should lead to minimal setup time. Some of the cons are the fact that the tip of the fin is hanging off of the ramp, not being super well supported. And so because of this, you need to be careful with applying even pressure to make sure that the tip of the fin doesn't warp or bend if you put too much pressure. And the other issue we looked at was the fact that because it's 3D printed, when it's resting on the sander or coming in contact with the fin, it might get hot and might warp. And so some of the things we looked at to address this are maybe printing out of more heat-resistant filaments like PETG, or maybe looking at a Creality 3D printer glass plate or something similar to take the place of the top surface where the fin's resting on, so we have a flat surface.
This is the second design that we've settled on. It models a traditional knife bevel jig, and the way this jig works is by clamping or attaching the fin to the angled portion of the plate. and then changing the sander to be vertical, and then sliding said angle portion into the sander manually. And then we will also, once we do slide the sander or the jig into the sander, you would slide it horizontally back and forth to reduce the inconsistency from the actual sander itself. The pros of this design are that the design is traditionally used for smaller angles, which will allow for a very consistent 4 degree that we're looking for. The horizontal motion will decrease the inconsistency from the sander, and the clamping to the solid surface would reduce that warpage that was one of the issues with the actual fin and heating it up. It's also a simple print design that will be able to print pretty easily and go as one piece. The cons of this is that the attachment method might not fit with the jig. And to get around this, we'd have to measure how much room we have for attachment at the bottom and what other attachment methods we could use. Manually pushing the jig into the sander could create some variance, and there's no way to currently stop the distance that the fin gets grinded. These both could be solved by adding some sort of hard stop that we can slide the jig into in order to create a consistent line that it's moving and the distance that it sands. Okay, so here's our third bevel jig design. And how this one works is you have a large 3D printed block, and our fin gets clamped into the block with that orange 3D printed piece. There's a bolt that goes through the block, and it's angled so that the orange 3D printed piece is pushing the fin securely into the block. Then the block is held by hand, and the belt sander is put in a vertical position, and it's moved side to side along the belt sander to sand our bevel. And now going on to some pros and cons of this design. It's very simple. It's 3D printable, so it's easy to manufacture. It gives us a very accurate bevel angle. It's very sturdy because it's a large 3D printed block. And the way we would figure out when to stop beveling is by measuring the width of that bevel with calipers, which would not be difficult to do. The cons of this design are that we would need separate bevel jigs for, but it would be the same design. We would just need a separate version of it for both the leading edge bevel and the trailing edge bevel.
Okay, so now onto molds. Our main goal is to be able to design and fabricate our own custom molds of a nose cone and the transition mold to be used on the rocket. And we have the requirements for both molds that we want them to actually produce the desired shape and also have also visual floss. This way we can ensure a successful integration of the parts. And also we want our molds to be able to withstand the manufacturing process and also yield a smooth surface finish when we're done.
Okay, here's the nose cone mold overview. And what we want to do is we want to use a traditional composite mold making technique with a 3D printed nose cone plug. And if you look at the picture here, that orange right there is a parting plane. The dark material under it would be laser cut plywood. That would be a supporting structure for the parting plane. And the 3D printed nose cone plug would lay in that. We would apply a mold release on top of it. Then we would apply a gel coat to give us a super nice finish. Then we would apply our composite layup. That would be half the mold. Once that cures, we could take off the parting plane of the supporting structure, flip it over, and do the other side. So here's some of the procedure. Like I said, doing it in 2 separate parts. We would be traditional composite layup for both sides, and that would give us some really good finishes, some really good durability. Going more into the pros and cons, like I said, surface finish would be directly mirroring the plug, so we could spend a good amount of time making the plug very nice, and that would translate to the mold. Secondly, our mold is going to be very strong because it is just composites, right? And that would allow us to do future manufacturing processes like autoclave or heat for curing. The mold would be very long lasting. It can be used for years and years because it is composites again. And like I said, it can be cured with heat and other types of curing techniques like autoclave. So some of the
Cons is it is a bit more labor intensive and it does take some more skilled labor to produce it, as well as being slightly more expensive than just using something like a 3D printed mold.
Okay, so onto the transition mode. As previously mentioned, there is a small 1-inch difference between the diameter of the sustainer body tube and the booster body tube. Thus, that's why we need to make a transition body tube to make a smooth transition between these two body sections of the body tubes. And the procedure that we use for the transition mode is the same that we use for the nose cone.
So we have some additional manufacturing planned for later in the year. The first of which is fillets for the fin can. Fillets are the material that bridges the gaps between the fins and the tube itself. The fillets help to increase the aerodynamic efficiency as well as the structural integrity of the fin can. We plan to create the fillets using sort of a two-step process of an inner fillet and an outer fillet. Both are constructed using epoxy mixed with silica powder. The silica powder and epoxy is applied to the fin tube and shaped using a fillet tool. The initial layer is built and then just shaped with the fillet tool. The outer layer is placed on top once the inner layer cures, and then is shaped using a fillet tool as well as a dowel, which is placed on for the initial setting process in order to maintain the desired 1-inch radius. As well, we also have layups, which is a means of increasing the structural integrity of the fin can. We use a wet layup process that includes the stacking of composite layers of fiberglass in a 90, 45, and 90 degree orientation. I have some pictures here of some practice layups that we've done during A-term. And then as far as the procedure, it includes applying a layer of epoxy to the fin can, applying the layers of fiberglass, and then layers of peel ply and breather layers, which then help to secure the layups in place. And then we vacuum bag the entire fin can for even distribution of pressure while the layups cure. Forgot what I was going to say. Yeah, the entire thing's vacuum bagged for even load distribution. I have a picture here showing an example of a fin can that is vacuum bagged. And that is all. Questions?
Nose cone. Have you guys thought about figuring out like putting a tip on it or anything?
So as far as that goes, we haven't got that far ahead yet. That's been outside of the scope of our model. But we are going into the next few weeks of E-term when we finish up the model. We're definitely going to consider doing that and look into that and how it would benefit our model.
Yeah, it's not going to be necessarily, we haven't decided on aluminum, but we are not going to have the composites go directly to a point. It's going to stop a little bit before, and then there's going to be something, a little tip that screws on because it's just much easier to mold it and do the layup when it doesn't go directly to a point. So yes, we will.
I know you talked about like post manufacturing like testing that you're going to do to make sure that the right specifications and tolerances. How is that going to work for your fillets and your
So the fillets, it's a pretty standard procedure making the fillets, and it's been tried and proven in the past. And there is not much testing that needs to be conducted to ensure that they, I guess, work. Are you referring to the material properties of?
No, the physical dimensions.
Yes, so the physical dimensions are just standard. And the angle for the leading and trailing edges, that is something that is not, we are not calculating.
Are you measuring the exact angle? This is for jig number 2. Are you planning on measuring the exact angle as you stand? Are you gonna stop measure it and then put it back every time? But if you go past the 40 degree?
Yeah, well, the jig for number 2, the actual angled plate is already at that 40-degree angle that we need. So the bevel, yeah. Thanks. Yep, so that angled portion on the first model is already at the degrees needed. So it just comes down, the actual angle of the bevel will be correct, but it comes down to the length, which I need to make a hard stop to be able to kind of get to the right length. As of right now, I don't really have a way to stop that length, but that's what I'm working on to fix.
Slide 36. I just had a quick. So you're gonna perform FBA on the fin cans. Is that like the entire can with the fins? Okay, like the entire structure.
That is a big reason why we are using Abacus over ANSYS, because you can use these partitions to separate all the different materials, all the different parts of the entire fin can, and individually and then also collectively simulate the fin can.
Edges don't cause rocking of the sand. So I assume this is bevel of 1, the trailing edge, how are you on the leading edge without it being affected by the angle?
Or is jig?
This was slide 39. Just in the diagram on the right where you have the fin kind of in the jig, if the bottom side is bevel. What this is being. Oh, sorry, I was thinking this was gonna be flipped up on top. Okay. Okay, never mind. I was good. Could this jig be made out of aluminum? I know you're thinking hard material.
I mean, that would be a lot of material. I think first we're gonna probably test one out of 3D printing, see how that works. If there's a lot of problems, we did look at some other materials. The one that came to mind was using maybe a glass plate or something similar, like a Creality 3D printer plate on top of basically this surface, so that even if the 3D print comes out a little uneven, you can put something on top that's a flat surface, so the fin always has something to rest on and have good contact area. Yeah. I think, yeah, aluminum would cost a lot and take a lot of ops, but.
3 parts, right? 2 sides.
Is there are several parts of the jigs and also the nose cone plug specifically that are 3D printed. And I'm wondering what tolerances you're expecting for that. Specifically for the precision of the fins, and also if you're building a nose cone and something's supposed to go inside of it, which I'm not sure like what the situation is for things going inside of nose cone. I know you definitely have the past. What sort of tolerances are you expecting?
Want to answer the jigs at all?
Sure. I don't think we have an exact number on the tolerance because we haven't worked with the printers and used these printers at WPI yet. So there's going to be a lot of testing and measuring after to figure out what the tolerance and how far off we are from the desired geometry. But that's something we're going to look into and make multiple tests and iterations of each design before we go forward with the final composite.
It's to design that nose cone plug, for example, if it can't be 3D printed.
If it can't be 3D printed, it could be machined, but because it's cylindrical, it makes much more sense to 3D print it upright, and it should be it should be plenty accurate on a a well-adjusted 3D printer. The other way we could do it is we could machine it upright as well, but it wouldn't really be justified because there's extra cost, extra complication, and not a whole lot of extra benefit because we get it so close with 3D printing. And to answer your question about the inside of the nose cone and how we're going to get the tube to fit that we're sliding in, is that what is it?
If you have things that go inside the nose cone, that's part of the payload a lot of times.
Mhm.
Will sit partially inside the nose cone. What if your 3D print isn't tolerance exactly what you want to, it's going to be affecting everything that would have to fit inside.
Yes. So also, like, I think I get your question. The inside of, like, the inner diameter of the nose cone would just be affected by our, like, composite layup, how thick we make the nose cone, right? Is that what you're asking?
The big J signs have the same issue of manual pressure being a potential issue with some like potentially thinner on one side. I didn't see any jig that had a way around that. So is there any thought process on that?
Well, we are hoping for some feedback from you guys on maybe some other ideas that we haven't thought of how to approach that. Moving forward in B term, we are looking into those solutions. If you guys want to talk about things that you thought of.
A few of the things we looked at were, for example, with this design, having a surface that clamps the plate and maybe rests, and that clamping plate or structure rests on the fin, so you're not directly pressing the fin down onto the ramp, onto the belt. And that's could be something that maybe rests on rollers or some sort of linear rail mechanism. But for PDR, we want to bring some simple designs that were mostly, as you can see, one piece. Start with something simple and then get feedback for how we can improve.
It's like, I like the idea of clamping, but like also that's just like there's some extra amounts, so like they sell clamps that are tension similar to like torque screws, or large screwdrivers with like eccentric circular. So like maybe looking at something like that, something like down the same with the screw to fit.
Very good question. Talked a lot about like simulating and testing the fins. Are you planning on doing something similar for the nose cone? Like, how are you ensuring that the nose cone will be structurally sound?
Well, that's a good question and something we'll look into more. But as of right now, I'd say that the loads that the nose cone is under is much less. It's able to handle it much better just innately because of, it's a point and it's a simple shape and it's not going to be under the same kind of like varying and dynamic stresses that the fins are going to be under. And we're able to make that composite layup thick enough that we could do some calculations on that, but we're basically just able to say, all right, it's pretty thick and the expected loads are going to be, it's going to be able to handle them easily.
Additionally, we will be conducting thermal analyses on the fin can, but also we'll be planning on doing thermal analyses for the rocket. So that is more prudent for the nose cone specifically.
Off there.
Yeah,
I know, but oh, that's actually. It is what it is.
I think we need to take a.
Step forward. Like used to the tape.
The bowl.
We can see the speaker names.
It gets.
They'll be here. Hope so. Hope so. We'd have to.
You guys can start whenever.
Okay. Hi, we're 30K Rocket Structures, and this is our preliminary design review. This year, our structures team has been working on two subsystems, the motor retainer and the payload couplings. The nose cone coupling is attached to the inner flange of the nose cone as well as the payload bay. The payload recovery coupling is bolted to the airframe and attached to the payload recovery bay. The motor retainer is attached to the bottom of the fin can and will be covered by the tail cone. In the past, our team has also designed a ballast system, but since weight is a serious consideration for this year's project, we will not be having one. Some of the biggest objectives of our team is for payload components to have a straightforward integration and to ensure the motor is fastened in the rocket.
So first, we're going to talk about the motor retainer. I'm Ronan.
I'm Devin.
Alex.
So the main priorities for the motor retainer are to hold the weight of the motor before liftoff. However, we also need to make sure that the motor will stop from shooting up into the rocket. We need to choose a design that fits inside the 5-inch body tube and fit within the tail cone. With that being said, the tail cone must also still be able to attach to the rocket. Other priorities include a goal factor of safety of 1.8 and to keep everything as light as possible so that way we can achieve our goal of 30K.
Oh, there we go. Yeah, that's right. Okay. So going into, oh, the slides are being slow and now it's in like 2 seconds. Is it back? It's back. Okay. So the first design that we explored was using an Aeropack retainer. So this was used last year. It's a 2-piece system. The Aeropack body, which is the blue piece on the top right, is fixed to the rocket. And then the Aeropack cap, which is the gray piece on the very top, screws onto the body to secure the motor via just a big set of threads. We're currently researching the pros and cons of making this in-house versus purchasing it. So I'm going to talk about some of those. So for making it in-house, some of the pros that we talked about was, for starters, it's a learning experience. You're making it yourself. It also allows for more customization and opportunities for weight reduction because we're able to design it ourselves, and also more likely to fit in the tail cone because we can create the dimensions ourselves since we're designing it. And then in terms of cons for making it in-house, we're going to have to pay more attention to designing for manufacturing. We're also going to have to spend time manufacturing. And then we're also going to have probably larger tolerances because we're less capable of manufacturing it versus a professional company. So, and then for purchasing it, the pros of that, easier manufacturing process. It's a method that's worked in the past. Some of the cons of that, it might not fit in the tail cone since the dimensions are fixed and we can't edit them. And also there's less opportunities for weight reduction.
So as an alternative to the Aeropack retainer, we were looking into different methods for plate retainers. Some of the ones that we found online were a little small for our dimensions, so we kind of had to design this ourselves. This first one is, I call it like a wedding cake plate retainer because it has different tiers that get progressively smaller as you go up. There's 2 plates that are bolted to the thrust coupling. And there's standoffs between the plates and the thrust coupling that allow us to extend the plates outward into the tail cone, so we can take advantage of this, of putting the motor farther out in the tail cone. This will be most likely be a lighter option than the Aeropack, since the plates are much thinner material. And these are obviously much easier to manufacture, just a few plates, than if we were to try to make our own Aeropack retainer. It is a little bit more complex because there are a lot more pieces to this than, you know, just having the main body of the Aeropack and then screwing on the cap after the motor's inserted. But like most of this can be assembled beforehand, just building up the entire first layer plus the standoffs for the second layer, and then we can just insert the motor, slide the second plate on, and fasten it with hex nuts, and then fasten the tail cone afterwards, which is probably gonna have to be the case, just given the dimensions of the tail cone and the retainer that has to fit inside of it. We will probably have to just do the tail cone last. Yeah.
Okay, and so the last retainer type that we looked into was making what we called a tail cone plate retainer. It's essentially the same as the wedding cake retainer. The only difference is that the smallest plate, my mouse can, no, it's not, okay. The smallest plate is fastened directly to the tail cone via epoxy, as opposed to using standoffs to connect the larger plate and the smaller plate together. So it's less parts than the wedding cake. And it also, a potential concern that we have is that the epoxy might just not be strong enough to actually have enough support. So yeah.
Some of the future steps we're looking into for the upcoming term is we would like to meet with composites so we can work on actual tail cone integration. The last design that we just talked about is obviously completely dependent on talking with composites and figuring out how feasible it is to integrate. And then we need to do a lot of hand calculations and stress simulations in ANSYS, which we have not had time to do yet, but that will be done pretty shortly. And then hopefully we can work with composites to figure out how we're attaching the tail cone and work on selecting a design to begin manufacturing.
Hi, we're Payload. My name is Amna.
I'm Ricky.
I'm Jaden.
The design requirements for the nose cone coupling and recovery coupling is to fit inside the body tube of a 5-inch inner diameter. The goal of the nose cone coupling is just to connect the payload bay to the nose cone. And the payload coupling will be connected between the payload bay and the recovery to protect the payload from the pressure changes due to the ejection charges. The couplings will be lightweight to optimize the flight of the rocket to 30K.
So for the nose cone coupling, we matched the general geometry from last year. So we'll machine it on the CNCs at aluminum. And this year we removed the inner ring that we had last year to minimize the weight. We could also remove the material under that supports the mounting holes, but that would require a more complicated machining. We also have the same clocking feature as last year to align the bulkhead, and it's held in with spring pin holes and also epoxy, which is the same method we used last year.
For the recovery coupling, we're also matching last year's dimension and general design. We're also using the same CNC lathe for manufacturing, and it's made out of the part is made out of aluminum. Sorry, the gasket is laser cut standard silicone. The glocking feature helps align the coupling and the gasket. And the coupling is fixed using bolts and epoxy.
So future steps for our couplings, we still have to do von Mises stress simulation in ANSYS, and then we will start doing calculations. There's a screenshot of example calculations from last year. So we'll have to calculate the epoxy shear stress, radial bolt shear stress, and simple and complex tear out. And then we can start manufacturing and then pressure testing on old rocket couplings as well.
Okay, that is all. Thank you for your time. And are there any questions? Yes. Wait, hold on, it's being slow. This one? Okay.
So that green, green, it's like epoxy.
Yes.
Yes.
Are you gonna make sure it's like the right distance?
We haven't,
So.
yeah, sorry, this is a design that just kind of like popped up last week. We started talking about it, so we haven't really looked too far into actually figuring all those little things out. So we don't have an idea for that.
And same thing with the other one. You need to make sure that's like right price and mass.
Yeah, we'd have to look at the inner diameter of the tail cone to see, and also the correct dimensions for the outer diameter of the furthest ring to make sure that it like aligns correctly so that there's 0.5 inches in between the plates.
Please, you guys attach the body and then you guys have this.
Okay, so we haven't spoken with composites yet, but the easiest way that we're thinking the tail cone would be attached is radial bolts. For this coupling, or the thrust coupling we designed for this design, might not be so feasible to have radial bolts, but I think the AeroPack thrust coupling had a thicker ring at the top for radial bolts.
And just like a follow-up to that, just for some of you guys to pick that up. So you have a molding that looks all like we make it. Theoretically, like you guys need more space for radial bolts, that larger. Actually, could like the component and then it extend to like almost like a body tube for like maybe like a quarter of an inch.
Okay.
So you guys thought about composites, but like adding that quarter inch from body tube just in there for them. So like if that makes it easier to radial, because the way that looks right now, it's like it's still curving.
Yeah.
So this is like the whole thing. So it might be worth adding that a little bit of body tube.
Okay.
This is a very brief question. Do you have any plans to do calculations on number of radial bolts or what sort of? I'm mostly thinking one of the big reasons we get weeks off at IREC is for damage that's not easy to fix upon landing. And if you're landing on the tail cone, obviously assuming that the tail cone itself maintains a structural integrity, which is not really involved, we want to make sure it doesn't come out of the body tube. So I guess, is there any thought to your calculations for that?
That would probably be something we simulate when we do simulations in ANSYS. Clearly, we don't have any radial bolt holes on our design yet. So when we do our simulations, we'd look into different amounts of holes.
I'm just going to suggest the computers that we built last year would be probably really good this start.
Okay.
Question about Deva? I don't remember if I mentioned this to you guys, but you guys thought about like we could theoretically like 3D print the tail cone to like do some interior geometry because like we let's prove that was fine. But the tail cone is 3D printed. Yeah, so the Rocket tail cone was pretty smooth and we're fine. I feel like we're going much faster, so they're all fucking smooth and so then we should we can solve the position. Smoothing 3D print. So something for you guys to consider too, like if theoretically, we could make some geometry inside the tailcone if we go with 3D printing, where it would kind of adapt to whatever metal parts got there, but some of it, I'm gonna get some of it.
No, we haven't.
You have some more questions?
I just have a question because I don't know how it works. What forces does the second plate here like experience?
This, like the one on the bottom.
I really like the red one.
Okay, so like it's hard to tell, but it's like upside down, I guess. So when the motor is put in the rocket, that red plate would be secured to keep it up there.
Like the force of the motor is going through like the fluid.
Yeah.
Plate,
Yeah.
And that's just to hold it in, like carrying it around. The red plate is.
Kind of, yeah. Yeah.
Oh, yeah. So let's see what the bonds.
Especially under injection.
Oh, okay. Okay, thank you.
I have one, forgive me if this is redundant, I just can, but can you go to the slide of the other concept with
This one?
Yes.
Okay.
Or
the aero pack? Okay.
So, yeah, the one you're on.
Oh, is it? Wait. Sorry, it's like that's not okay.
No, not that.
Oh, okay.
The one with.
No, I know. I clicked it and I'm waiting for it to. Okay, there it is.
No, one more.
Oh gosh.
I noticed like.
Oh, wait, what?
No,
yeah. We got it.
This one, okay.
Okay, so, any kind of, epoxy joint in proximity to the nozzle, there would be thermal concerns or, loosening of that. Have you looked into that at all?
No, we haven't, but I would assume what Matt just said about the 3D printing, the same would go. So if we were looking into epoxy or I guess in terms of this design, I think this would be something that we'd be able to 3D print if we wanted to move forward with it. So that kind of did not answer the question, but no, we have not looked at thermal concerns yet. Yeah, go ahead.
Yeah, so one of the things about this design is that because the tail cone gets smaller as you go down, we're expecting most of the forces to be directed towards the aft end of the tail cone, which is gonna, like, if we have the plate designed for the, I guess, the diameter of the tail cone where it's currently sitting, then it won't be able to go farther down because it'll get stuck inside the tail cone.
Oh, I see.
So it kind of prevents it anyways. The epoxy is more of just like, I guess, extra precaution, but it shouldn't be able to move regardless, just because the geometry of the tail cone.
To saying this together, so this is some investment company.
Okay, so we had the rocket couplings last year because there were air brakes, but we don't have air brakes this year. There is a separation in the body tube, but since it doesn't need to be blocked off or airtight because there's no like changes in pressure, I believe we're just using inner tube to connect the two separate body tubes.
To add like a comment / question on the previous like thermal consideration question. My question being that plate would never be touching the nozzle directly with it.
No.
In that case, just a comment too, because it is air gap in that sense, if you're using materials like G10, fiberglass, or something along those lines, we wouldn't have that much of thermal consideration more than the casing itself contacting whatever surface on it. The casing, because of the liner that's inside of the motor, won't be experiencing temperatures higher than, like, it wouldn't burn your hand if you were touching it right away after, but most of the materials will handle just fine, especially the air gap.
Okay, thank you.
Guys?
I haven't decided yet.
What's that?
So you know what the like. No, that's getting. Oh.
Let's all do that. The city. The city. I have to make progress.
I started it for it's being recorded. Oh, I should. I did not play because I only saw the last. So I don't know what. This morning. Oh, like that's not. But I really. But I did not time. I don't think. Because I was planning to so that was.
Yeah. They did that.
And so positive. I'm in city center, like, how, you know, my like maker space. Yes. And I used to this. Audit attached to
Hey, did you remove the rocket?
Nah, it's other stuff. Like, unless I can like.
Did you remove the rocket?
I guess it's can you sound to get me out?
Right
now.
He's on his phone. All you have to do is slack him. I did not edit anyone's flag, so maybe it's back. Maybe it was. No, you can't start yet.
Nope.
Maybe until your time. You guys have another 5 minutes.
Yeah, like.
No, 5 minutes. You take another 5 minutes.
Oh, yeah, like that.
Well, we need Darius too. Oh, I'm in the mic.
Did Darius come? He's on the line.
Oh, yeah, we need the second 5 minutes. But.
You know what a bubbler is?
Water fountain.
There's a water fountain in there.
Not from Massachusetts.
If that's what you're looking for.
That's the term in Massachusetts.
It is. I don't care. It's not.
All right, put your stuff out there.
Also formally dressed. Half of us are formally dressed, the other half are not. This is the most formal thing.
You should, at least my sub team, we all wore the HPRC shirts.
When did you order merch? Did I miss the merch order?
No, this was there.
Be like a flagpole or something. Yeah, yeah, same.
Yeah.
Yeah. You'll do the first slide. You'll do you'll do that. Who's getting
Oh, also, I added like.
Do what?
To wear suits.
Yeah, I added something to it. I forgot what I added though, so when it comes up, you'll see.
I did the stuff, but no, I just, I guess I will not embarrass.
I was also not there.
I messed up. Unless it's like your junior or senior, then maybe you have to. No, yeah.
What? People
Yeah.
who are have suits, who have suits.
Yeah, I want some merch.
Posting. That's why I can merch, Brad.
I think I'm gonna group it.
Oh, well.
No, you actually have to make it working. You actually have to move the EPM for.
Yeah.
Listen, it for that.
Yeah, I heard about the house, like, I know about the whole thing.
It was showing
Also,
the animation. Yeah.
Yeah, what animation?
I just ended up doing that for things that like, I didn't know we had a deadline. I like.
Unfortunately. Maybe, or maybe.
I didn't really have a deadline at midnight. I was trying to, yeah.
Yeah, you're just like.
I got home at 11:30 and see that.
Guys, let's take a photo. Say GNC.
No, it's not. We gotta center ourselves with the screen. So yeah, shit that. We gotta center the screen, we gotta take a couple steps forward.
And off.
What you make?
That forward, that here, forward.
Okay, and forward.
A little more.
Keep going back, like he gets to the table. Okay, and also a little bit more that way. Strip this way, stop. You guys keep tripping. Hands down. That wasn't very bad.
I'm sure all of you practice sufficiently.
Oh, yeah.
I don't have a time, so just let me know.
Wait, you're lying.
These are. Those white pants. Where you go?
That's what I was saying. I don't know. Someone moved it.
I really hope it's like it's on load or something and no one deleted it.
No, I think it was deleted.
Yeah, I went to the border.
You guys are coming out. You can do all of that. You're saying. You're doing all of that.
Today.
Well, three.
You can roll.
Like three things.
Self-entry, visuals, map, future.
Oh, I'm talking about that. You guys.
I can see. Yeah, now.
Yo, I hope you guys like took a ton of caffeine. The two of you took like a ton of caffeine. I might have to.
Okay, would you like us to start?
Speed read.
We're missing our division leader.
Oh, that's true.
His car got declined.
Ooh, that's embarrassing. No, you're spending too much on Helios.
I want to get in the market. Maybe I'll go to tomorrow.
Thank you.
Thank you. Thank you. All right.
Okay, cool. Hi, we're GNC. I'm the sub-team lead, Rohan. This is a new sub-team this year, so I'm first going to go over our goals for this year and what we kind of we want the sub-team to do going forward. So first, we want to create a new knowledge base for the team and best practices. So first, developing simulations, whether that's VCAF or controllers or whatever it is, first in MATLAB, and then converting that to C++, so we can ensure that whatever algorithm we're doing actually works. And then additionally for this year, for our smaller projects, we're creating a canards testing platform on the Voyager rocket. It's a small rocket going to about 900 feet.
We are also developing a new state estimation algorithm called the multiplicative estimated Kalman filter or standard Kalman filter. And additionally, we are doing CFD and for the air brakes and the controls, as well as developing new guidance and control algorithms for canard attitude stabilization and air brake control. So timeline-wise, that looks like, so for this last term, we designed the canard hardware, and we developed the multiplicative ECAP and control algorithms in MATLAB. And then for this term, we are looking to deploy the multiplicative ECAP in C++ for the November 15th lift launch and have that as a first test. We want to finalize some of our control algorithms and test some of them for cost benefit analysis. We are going to perform CFD on the 2-stage and get that ironed out for our air brake controllers. And and then after that, make the actual controller in MATLAB and also manufacture our canard system for the Voyager rocket. C term, we're launching, and D term, we are going to do more work with the air brakes. Okay, that's off to Kieran.
Hello, I'm Kieran. I'm in charge of CFD for this year. And for CFD, we ran the canards, but in order to know what we are getting from the CFD, we have to determine the major challenges of installing the canards. And so the first major challenge is the mounting. How are we going to mount it onto the rocket, and what kind of forces does it have to withstand from when it's going up and like at its max airspeed? And then also we have to account for how the center of forces or the center of pressure moves as the canard deflects to actually apply a pitching moment. So in order to configure our computer simulation, we have to put 3 main parameters into the software, which is ANSYS Fluent. We put in the max airspeed, which we got from OpenRocket, and that was 271 meters per second. We have to put in the canard deflection angle, and we have to tell the computer what kind of equations to use. For the deflection angle, we did some research, and we found that a max deflection angle of 25 degrees would be optimal, as it provides about 70% of the max lifting force without encountering major forces or flow separation. However, there can still be a small amount of flow separation at 25 degrees. So to account for this, we're using the shear stress transport model for the computer, which is abbreviated to SST-K omega. And this includes equations to account for vortices that may form and flow separation along the edges of the canard. So after we got those parameters, we inputted them into the simulation. And this allowed us to get the max force and the max moment experienced by the canard. And that was both at 25 degrees. It was 72.9 newtons and a max moment of 1.74 Newton meters. Also gave us a breakdown of where these forces were coming from, such as if it was coming from pressure or from friction against the air. And here you can see some of what the actual simulation looked like. On the left-hand side, it's a 2-degree view of the canard at a 25-degree deflection. And you can see on the upper half, it's bright red because there's higher pressure there. On the bottom, it's blue for the low pressure. And then on the right, we have a 3D angle of it, although it's kind of difficult to see it. So now that we have this information, we need to use it to determine where exactly the center of forces is along the canard. So we use the equation, which is the change in position is equal to the force times the cross product of the moment reference point over the force. So this allows us to calculate the center of pressure. And this gave us a value of 23.6 meters back from the leading edge of the canard along the chord line. So this is about 45% back, since it's a 50 millimeter long canard. And then at 25 degrees, when we redid the calculations, gave us 23.1 millimeters, which is a good sign because that means it makes our mounting easier to account for since the center pressure isn't moving as much. with that, I will pass it off to the hardware team.
Hi, I'm Joe, and along with Noah, we did the hardware development for the canards. So kind of some of the guiding principles we looked at to shape how we approached this design. Because this is a new experimental subteam, we're operating under the assumption that a lot of things are going to change and a lot of things are going to break. And as such, we put a very high priority on modularity and adaptability to future use cases. We wanted kind of the core canards module to be something that can be used for projects that we haven't even anticipated yet, and be able to handle loads that we aren't necessarily expecting on this initial iteration. Also, to make life easier for the people on the software and controls side of things, we wanted to ensure that it would be as rigid and responsible as possible, both in the mechanical design and some of our electrical component choices.
So keeping those guiding principles and some of the hard design requirements in mind, our design architecture was ended up being a servo linkage that both allows for independently controlled canards. So each canard has can be controlled in terms of the degree and angle independently. That can allow for pitch control, but later on also roll control, and also pitch and yaw control if that's something we want to pursue later. It's again built into the proven Voyager rocket, which is a relatively slow rocket, but big enough to mount canards and not going too high up, going sub 1,000 feet. The individual decks of the hardware system are separated to allow for modular assembly and strength. So the servos at the bottom with a linkage going up to essentially a crankshaft in the canards level, and then the electronics and the flight computer sit on top of that. And the nice thing is, you'll see later, but this design allows for the individual canards to be assembled and taken on, taken off without having to disassemble the entire module. And so that allows us to potentially put different geometry canard, different size in the future. You can see the linkage animated in the Starting from the bottom, the entire system will be powered by 4 18650 batteries, so about 7.5 volts, which is more than sufficient power for the servo we chose. We're going to be using COTS battery holders. And one thing to note is that the batteries are horizontal, so that when the rocket accelerates upwards, we're not going to lose contact with the battery leads and get wonky results from that. The batteries themselves are offset to allow for fastener clearance and for mounting accessibility in order to mount the actual connect the two decks together. And then in the middle, there is a switch and a little channel for wires to go up to the switch, power wires to go up to the switch, which then go back down to power the servos. This 3D printed piece here is another, is both constraining the subsystem as well as providing mounting positions for the servos. We've got 4 servos that are arranged in a circular pattern. Highlighted there is where the servo sits and where the cutout is. And the little divot is for wire clearance to allow for wires to snake up and around to the switch and then down to the batteries. And one thing to note is that the profile is radially constrained using this 3D print. So it'll probably be 3D printed out of something like PETG. Depending on how much weight we're using, probably 20, 30% infill. We haven't done the exact run the numbers yet, but the weight should be pretty manageable, and the thing is pretty tall, so it should counteract any bending forces and stabilize the system. The servo we chose is this RS100 micro servo. We did look at several servo options, but this one stood out to us because it had a pretty high torque, especially for a small size, about 1.4 Newton meters when it's running at about 7.5 volts. It is geared down because of the, if you'll remember, the CFD forces, the max moment was 1.74. So Joe will get into this later, but depending on the linked geometry and what angle that this is geared down in order to provide mechanical advantage for the servo to power the canard. But other things that we really loved about the servo was its actuation rate, being able to do 60 degrees in roughly 0.06 seconds. And on the right is the motor curve that is plotted roughly estimating how long it would take in worst case scenario to do 50 degrees of plus or minus 25 degrees of motion. It's running about 140 degrees a second. That's the slowest it's going to go, which would take about 0.35 seconds to sweep from minus 25 to 25 degrees. And another other things about the servo we really liked was that it had all metal gearing, so no plastic parts transmitting power like a lot of other servos had. And the servos themselves are about $40 each, which is about standard for this size of servo in this form.
All right, so moving on to the canards level, in taking into account the numbers we were getting from CFD, we did a quick shaft bending analysis to make sure that that normal force wasn't going to deflect things. This is with a 3/16 hex aluminum profile, which you'll see the reasons for that on the next slide. And you can see the deflection under those loads is really trivial. It's not a big concern, but it's nice to have the system overbuilt again for if you're going to be using potentially larger canards in the future. And also, as we'll see, there are some practical reasons that set kind of a minimum size to this shaft. So the simple solution would be to have your shaft built into the canard and just connect the linkage assembly directly onto that. But in practice, that would be really difficult because anytime you need to replace the canard, you have to take apart the whole linkage and undo shoulder bolts and such and take things out of bearings, and it would be a whole procedure. So we wanted to make it operationally much more simple, even if part-wise there's a bit more going on. So we came up with this female hex sleeve design, where if you look at the linkage, the shaft that it's driving is actually a hollow hex profile that then interfaces with the male blue hex profile on the canard. And that is retained in place by a set screw that is captive in a groove. So you can, without doing any further disassembly of the system, just loosen up a single screw, pull a canard out, replace it, and you're back in business without having to take the system out of the coupler tube, take anything apart on the linkage or anything like that. You'll also notice that the pivot point is forwards of where we calculated the center of pressure. That is intentional as a failsafe. That is so that if there is any kind of electromechanical failure with the system, the canard has aerodynamic stability and it will tend towards pivoting towards a zero angle of attack position. So you're never in a situation where the canard is locked in a position where it's giving a strong control authority command that we did not intend. So getting more into the cross section here, you can see the dark blue would be that canard shaft, and the gray kind of stepped profile there, that's the captive hex sleeve. That's it's just geometrically constrained between the bearings on either side of it. And the reason that set kind of the minimum size for it is we didn't want to have to buy an expensive brooch and then abuse that brooch by making a hex hole several times its diameter. So the sleeve is turned out of its COTS extrusion of aluminum that you can get, and 1/4-inch hex internal is just the minimum size for that. And then the orange part is this link right here, which is your rocker link, the other side of the linkage. That would be press fit to the core sleeve with a Loctite 609 to get a solid bond. Yep. You're using M3 shoulder bolts for the pivots, and we have absolute encoders directly on the canard shaft for feedback. We use the US Digital MA4. The whole structure is held together by these two parallel aluminum plates. There are kind of inevitably some thin sections in these 3D prints, so passing some of the structure onto those parts helps with that. The electronics level, which we haven't really gone into yet, is basically going to be just standoffs above the canards level. We will be looking more at that in B term. And then here's a quick graph showing how the linkage geometry and the fact that your servo horn crank is shorter allows for mechanical advantage that actually improves as you increase in angle of attack. So you're within the numbers that we're getting from CFD.
Hello, I'm Colette. I'm going to give a very quick overview of just the Simulink modeling that we're going to be doing to do full pipeline simulations from launch to controls. Essentially, this is a Simulink model. It consists of both the plant model, which for those of you who aren't familiar, models all of the natural rocket dynamics. But the piece that we're going to be most interested in is the flight computer itself. So this is going to be where, for modeling purposes, we implement the sensor fusion, which these guys are going to talk about in just a second, our guidance algorithms, and our canard actuation commands.
I'm Shreya. I was one of the people working on the MEKF. So previously what we used was something called an additive extended Kalman filter. So it linearized a system that was nonlinear, but this had problems because the system lived in a 3D vector space, so it didn't really take into account quaternions, which are needed to solve gimbal lock. So our solution was to use the MEKF instead, and this would introduce quaternions and add a degree of freedom.
Yeah, my name is Darius. I also worked on the MEKF. Just sort of extending on this, I don't really know how to play the video. But basically the reason why we have an MEKF is because it simply is a means to an end. The importance behind it is because the end goal that we want is to have a reliable estimation of where we are, because knowing where we want to be is only one half of the equation. The other half is knowing where we currently are. And knowing this allows us so that when things go wrong, because they inevitably will go wrong, we know exactly how they went wrong, which is actually the important thing. So over here, it allows us to have our estimations. We can have it in quaternion format. We can have the Euler angles derived by it. If the video would play and animation will what? Oh yeah. All right, so obviously knowing where we are accurately allows us to do cool things like actually modeling it, whether it be in 3D. More importantly, we could actually plot our expected versus our realized outputs or our states. And knowing this, again, when things go wrong, we know what to account for, what we need to improve in the future, as opposed to our past time steps and our current and future predicted time steps.
All right. All right. My name is Abe, and we're talking about EKF math. So basically over each time step, we take in our measurements and we need to use how much we trust each measurement and combine that in a very mathematical way to give us what we think is our true prediction. So if you see, the first equation goes into just predicting our next time step. And then we propagate the covariance, which is how much we trust that. And then we calculate on the right something called the Kalman gain, which is how much we trust our sensor versus how much we trust our initial guess. So using those covariances, we get that value, and then that tells us how much to trust our initial prediction versus our sensor measurements. Okay. So here is how a MEKF, which is what we do, is different. So if you look at the first equation, that takes in the angular velocity from the gyroscope and then integrates that over time, just multiplying by delta time. And then getting into quaternions, we convert that into a quaternion, and then we multiply by our old quaternion to get our new quaternion. So basically just taking how much we rotate and then just rotating our estimate by that.
The second step is our vector measurements and correcting based off that. So we rotate by where we think we are and we compare what we're reading in our magnetometer and our gyroscope compared to what we should be reading at that direction. So we compare it to that. And like I said earlier about the Kalman filter, we can compare what we think versus what we have and use the covariances to tell us how we should move forward. And then another difference about the MEKF is that we actually model our errors instead of the actual state. It's kind of complicated, but basically it's just easier to model the errors instead. So then we just add the errors back in the end to give us our state.
Hi, I'm Chris, and now that we have our MEKF working in the MATLAB and in the simulation, we intend on implementing it into C++ by November 15th for the lift rocket. And we also need to make it more accurate and more robust in doing that, so that'll be nice. We also intend on using multiple IMUs in the rocket, resulting in nice sensor fusion and even better state estimation.
I'm going to go over the guidance and control systems very quickly. The guidance system is very straightforward because we want to stabilize the rocket. All we want to do is ensure that our roll, pitch, and yaw rate is 0. And so essentially, if those aren't changing, neither is our rocket. Some of you may have questions. If we start out at like a pitch of 5 degrees, can we correct for that and make it 0 degrees? No, we cannot, because that is not stabilization. So very straightforward. For a control system, for stabilization purposes, proportional integral derivative controllers and or the active controller is pretty straightforward and a good way to do that. If we have extra time and we want to be crazy about it, we can do something like a linear quadratic regulator, LQR controller, but that will come in time. Just to give an example of what this implementation looks like in MATLAB, it's pretty straightforward. Well, technically this is simulating, not MATLAB, but all we do is we take our current pitch, yaw, and roll, and we feed it into our PID blocks, which will then output our attitude commands. This is a little bit of a better representation of what is inside the PID block. All this block does is it represents the equation below, which is our classic PID equation, which I'm sure many of you are familiar with, but all this does is it corrects for error between our required and our current estimate.
I know we had a lot to cover, but are there any questions in our 5 minutes?
In general. Okay.
Yeah, so you mentioned the thing about having the pinpoint above the pins that it kind of pins down. If one fails though, wouldn't the rocket still start to couple with the other since they're all separately controlled?
I guess yes. Depending on failure mode, there are certainly failure modes like a power failure where you would expect all 4 would go at once. If it's something like one going, there may be ways for the system to identify that. You'd have to ask these people more about that. Hadn't been something we'd considered though.
So because we're using an absolute encoder, we always know where it is regardless of whether the motor fails or not. So we can know that, hey, one canard is at 0, and then the rest of the canards based on the control algorithm will fix that.
So they're all basically just
no, the control algorithm will still work, and it'll have an error of constantly at 0. And it'll, yeah.
It's like they
yeah, we can put that in the algorithm to identify that error.
Yeah, I was going to say, sort of related to that, I was concerned that in a situation where there's some sort of failure and they're still able to move, even though we don't have control over them, or would that never be the case?
So we can definitely, I think like a very simple solution is if we're trying to have like a very large error, like say we're trying to go to 25 degrees and we're constantly reading that the canard is staying at 0, meaning that the motor's not working anymore, we can throw in an exception and return them all to 0 and to just turn off all control stabilization.
So you're going to be controlling them live, or Is this all autonomous? Because what, like, so, like,
This is autonomous. I will not be sending messages from the ground station.
That is illegal. Have you guys done any analysis of the stability of the rocket with the added canards and that's
Not yet. That I will put that into something we will do for this term.
it'll definitely move the center.
Oh, have you, Joe?
I would expect it would be more stable just because you're adding a lot of mass to the
You're adding
nose.
more mass, but you're also adding more.
Drag.
Yeah, you're moving the center of pressure up too. Well, I don't know which one is.
I haven't done that specific analysis. My strong hunch is that the mass would outweigh the aerodynamics, especially because at a default zero angle of attack, they shouldn't really be contributing, but we will definitely look into that.
Yeah.
Okay, that's good to know.
And that was another reason for trying to make the canards and servo level independent, is make it so that if you wanted to switch to a system where like you have one actuator for roll control that's powering all four, you can do that without rebuilding the entire canard stack.
two simulations, which is you're using Open Rocket for one of them, and I just meant to confirm that the value you're getting from Open Rocket, you're using a simulation in Open Rocket that is accurate to where you're going to be launching, and not just some random settings in Open Rocket.
In terms of like atmospheric conditions, I think.
I don't know. Do you remember the specific conditions that you used for the Open Rocket? Because you used the Open Rocket for the ANSYS sim.
You don't know,
I think the only person who's looked at the Open Rocket is Mo, who
Yeah,
is
he is
in
on
Australia.
right now.
Okay, so I would just definitely say verify that number if it comes from Open Rocket, because there are a lot of things that,
Have you guys made problem?
yeah, absolutely.
Okay, thank you.
Yes. Joe.
Yeah.
Answer your homework. Dude, I forgot we had the other math slide.
Huh?
Forgot about the other math slide.
I could have done this first.
I'm blocking it, right? I get that forward. Well, yes, I hate it. Rude. Yes.
No.
I wish this one. Thank you.
Oh, that's my mic.
Yeah.
Kate, are we good? Thank you. We are Payload Lander. I'm our lead. I'm Aubrey. And we're just going over what we've done and our changes.
Hello, I'm Zach. So first, we're going to start with the payload system layout. So we're looking at a 40 centimeter tall structure. This basically goes over where each part is. So you have the parachute up there, the actuation mechanism, then the rover that will be deployed, the middle, and then electronics in the self-righting system. The self-righting mechanism is in the U closest to the nose cone, and the electronics just sit under the self-righting and the rover actuation under that system. The rover will have electronics attached, so they only need enough for the servo control in the system.
Our outer structure.
Okay, so for our outer structure, we determined that the ejection force was going to be about 300 pounds last year. And our important thing when designing a structure was going to be that it fit within CubeSat, which we are good for.
And then below we have a couple of our calculations that we ran. And yeah, so it just needs to be able to house like the rover, the actuation, and all the electronics, as Zach already said in the diagram before. So to do that, it's very similar to what we had last year, but we have 4 vertical L-channel beams, which are made out of aluminum. And then connecting them, we have horizontal cross members that are going to run up and down.
For the L channel analysis, they're based off they're basically last year's data. So as we said, injection force of 300 pounds, and we need a minimum factor of security of 1.5. So based on the yield strength of 35,000 PSI, we had a compressive stress. We had a compressive stress factor of safety of 15. So for good, yielding is not a concern. And with buckling force, we had 2.4 factor of safety. That was the lowest one, so that's good. And we have now channel simulation bending, which also yield a minimum factor of safety of 2.4, which is also within our minimum factor of safety of 1.5.
So if you saw the payload last year, we're making a few minor changes. Obviously, the main difference is that we are changing the location from being directly opposite of the nose cone from last year to now we are directly against the nose cone, which does bring up the dilemma of, hey, there's an eye bolt right there. So the way we went about attacking that was we got rid of the 4th paddle that we had last year, and we made that our ideal side for the rover. So if that makes any sense, if we're looking at this top photo, imagine the rover like in between the L channels with its wheels on the base, basically so that we won't have to rotate from the eye bolt side. We'll just have to rotate to the eye bolt side, if that makes any sense. We also chose some new servos, which Zach will talk about in a sec, basically so that we can actually use them. And then we are further into this term going to look at if it's necessary or helpful to have new geometries, whether that be with our gear ratios or with our linkage angles that connect our paddles and the main gear in the middle.
Talking about those new servos, we have a 5-turn dual mode servo. So we're gonna have 2 of those in the system, and the voltage range here is about 4.8 volts to 7.4 volts. And we found the max stall torque to be around 25.2 kilograms per centimeter at 7.4 volts. So we did some preliminary rough calculations of what the required torque would be, and we're looking at 5 kilograms per centimeter. So 25 is about 5 times as high, so we should be all good for that. So that'll further increase the force we can exert with the system.
Yeah, so seeing as we're not making many changes, that was a 5-minute presentation for your enjoyment. Do we have any questions? Yes, Amber. No, you're good.
So how much space is being given to electronics? Does this include batteries? And is the rover sharing power with?
So no, the rover, from what I understand, and they have their PDR tomorrow and they're still making a few final decisions. But from what I understand for what the rover is doing, all of their stuff is going to be on the rover. So they're not going to need to have access to any of the electronics that are stuck on the payload. So they'll have their battery, they'll have like everything they need, their servos and all that. So the only thing that's going to be electronics is going to be anything that's needed. I don't do electronics. So it's gonna be anything that's needed just to power the two servos we have and then control those. So from what I understand, that's like battery and a Mars board. So basically so when we did this, we allotted the 0.8 U that we had last year for self-riding. We allotted originally rover and actuation together can get 2.5 U, which then puts us at about 7 U left over. 0.7, yes. So we have the space. If we do end up needing less space than 0.7 U, then rover will get that space. But if we do end up using all of that, then we do have that space allotted. Okay.
Oh, I highly recommend.
Okay, we can look into that for sure. You're good.
Since.
Of course.
You said that you're fitting in CubeSat, which is great. Are you fitting within the 5-inch diameter of the body?
Yes, so the same idea we had last year with the L channels. They're in fact going to be the same L channels as last year because we can tell that they work, seeing as last year's payload is in my apartment. So some of it is in my apartment. Some of it's still there, but that's okay. Anyone else? Yes, Will.
To maybe answer Amber's question, maybe I'm misunderstanding. So I was thinking, unless maybe something changed, that so there's a board on the rover, right?
Yes.
And that is essentially telling Lander to actuate, or is there a
Yes.
board? So are you planning on having power? Like you could just have power run from the rover.
That is true.
To power those servos.
Yeah, because we won't need it after they
Right.
leave. Yeah.
If you're already sending, well, I guess the way you actuate the servos is the power, or am I?
That. Well, I would recommend looking into those design. Also look at all of the CDR comments in each of the document because there were a lot of issues with it, but they did umbilical designs. We could look into that system.
Okay, yeah, we can definitely look into that.
See, having to put like 2 batteries in there for like a second battery is would be, so if you can just power it directly.
Yeah. Yeah.
Anybody else have questions?
Yeah, you guys. Okay. We have the same question.
Yeah.
So there was an issue last year with the L channel being a lot of tolerance, which led to them not today.
Okay.
How they're made? Are they made the same way, just like some tolerancing a little more?
So my plan was to look at the machining process again and change some of the tolerances. Because Sophia did inform me about that. So the plan was to, instead of going off of the tolerances that we did from last year, go a few millimeters smaller, depending on how much it actually did. And then ideally test it in a 5-inch tube for everything's in it.
And so like we are still planning to machine them ourselves.
Yes. Just because it's most accurate and then we can put the holes where we want them.
I definitely like, if we could start that possibility too.
Yes, I'm ideally gonna hopefully start that this term, as long as I can get the stock in before then.
Is it possible to reuse the L channels from last year? Not so.
They exist, they're just kind of bent-ish.
You get what I do then.
We made them fit though.
No,
No, they are like this right now.
Okay, that's a different, they also didn't fit. We were. Ramming the payload down.
Yeah, but like not again.
Let's make it once.
Yeah,
Yeah.
plus she has a place in my apartment right now, Will.
Okay.
She's on my
I
shelf.
was just curious, so that's better.
Okay. Matt, you're the.
I'm good. Actually, I do have a question.
I think she's telling you you have another question.
Okay, for slide 111, I don't even know how that's going.
I'm going to it.
So if the self-riding is by the nose cone.
Yes.
Are you worried that so that when the nose cone lands, like, they're gonna be kind of tilted off the ground because the nose cone is wider than the L channels?
Correct.
So is there a worry that like, they're not gonna get to the ground where they should? Like, I don't know, like, so like if we're at home, not on like a flat ground, like they might be higher off the ground, like with the paddles can handle, I don't know.
So the paddles are each approximately 6 centimeters. So there's not. So it's not like the difference between the nose cone and the ground, like that distance there isn't it's not 6 centimeters. So I'm not super worried about that unless we determine there's a need to worry more deeply about that. Yes, Kate.
This may be a stupid question. What happens if they land in a bush?
We cry. Yeah, I was informed. Yeah, me neither. I was informed by everyone that this would have succeeded had we known how to code the servos and had we had a parachute that existed. So I have, and we'll do more testing this year just to confirm that. But I have no reason to believe that we will land in a bush.
Yeah, there's like one bunch of bushes, and if you hit that.
Yeah, again, cry.
But like also the certain division gave us enough space, we could have the parachute roller on there, so that would be pretty.
Okay, that's understandable. And also like, if you land in a bush, like, part of the mission will still be able to.
Yes.
Like, you don't
like drop
the rover will kind of just go.
You also still have ideally like a liquid ground station and
Yeah.
like you will still have some.
Yes. And honestly, I don't know how strong the bushes are, but theoretically, if it's a strong-ish bush, we can push against said bush. If that makes sense. I don't know.
Yeah, I would say most of the bushes, they were like shallow word. I don't know. They were
short.
They weren't even short though. They were like.
Am I shallow?
Like they were very Because like they weren't like thick at all. Like you totally could like when you landed it, you would probably like crush it. Like, yeah.
Well, we are lighter this year.
I probably will still crush it.
Nice. Good to know. Yes.
So this might be more of a recovery question, but so the parachute being in such close proximity to the paddles, do you have any concerns with, as this thing rolls, any way that might interfere with the paddles, whether I've heard mention of a removable parachute at some point, but even with that, whatever residual dangly bit from that mechanism would be in there, are you making sure that there aren't any interference paths to that?
So from what I understand from recovery, the most likely occurrence when we land is going to be that the eye bolt is on the top. Thus, when like in this instance, the most likely orientation would be flipped when we land so that the eye bolt and the parachute are towards the top of the screen. Thus, when we do end up turning, it should remain, like, there isn't a paddle there. So any rotation shouldn't interact, because theoretically, the parachute will be somewhat taut, not extremely loose. So there shouldn't be any dangly bits like you're saying. If we do testing, we do notice that there are problems with that, then I will talk to recovery and we'll be like, hey, what can we do? Is there an idea you have? We will go into solving that if that becomes an issue.
So in the, like, it would have to be like absolutely zero wind for it to just completely deflate all that, even though we are attaching part of it. Like I'm still envisioning that it's gonna be kind of blown around a little bit.
Yeah.
I think it would have to be like.
So still up in the air and not close to the paddles.
So like as you roll entanglement potential.
I will say, if you were to roll into it though,
It won't necessarily be a problem.
probably still good. Yes.
Add scissors, payload. I don't know.
You say that because we did that whole idea last year.
Oh, I love that for us. Okay, do we have any other questions?
Why did you choose such a strong?
So it wasn't so much about the strength. This was just the strength that happened to work. We determined that we needed about 180-degree rotation from our main gear that's centered in our self-righting mechanism. So using Owen's assistance, we calculated that it would need like approximately a full turn from each servo, a full 360-degree rotation, and only, or no, it was more than that, wasn't it?
Almost 500.
It was almost 500 degrees. It was like 470 something. And so it was mainly deciding using a servo that could do that amount of turn without staying continuous, because that would add more difficulty with control.
So this just happened to be the cheapest option that was.
Not necessarily, but the best one I found on Servo City, because that's the place I would recommend it. I look.
Yes, and that's the place. I was just curious about the 5 times the strong cheaper option.
Yeah, it's the strength isn't what it was. I was trying to get something that had like just enough but wasn't overkill. It was either like 180 degrees or the 5 turn where it said like 1800 degrees. And I'm like, I need more than 300, and I need more than an 80. So I guess I'm going to 10 more. Yeah.
The questions?
They want to take a break, Kate.
Thank you.
You're welcome. Have a good night, guys. Oh, thanks.
I know. And yes, and the day before. You did this for yourself, and that's the whole goal.
That's why we get enough people in the home.
GNC. Ground Station is gonna be the last one tonight. One of this is actually going tomorrow now, the same, because.
Yeah.
Yeah, yes. Yeah.
No, it's not. So now,
Well, everyone celebrates the limits are really. I think 960 is still fine.
Yeah, it's also earlier.
Where's the dish?
Where's the dish? Wouldn't you like to know, weather boy?
What? Look like you're going here first.
My friends.
Remember, it's the whole thing.
Hey, there's a.
Secrets, like business, value.
I'm sorry.
I'm sorry.
I don't, I'll have it sound. Matt, cut this. Yeah.
Oh, the interview was not, the interview was okay. No, I'm thinking it could be like 4. In a row.
No. Oh, no. That is literally the exact opposite of what I want. Yeah. Yeah, that's well. Sugar free. Me too. Yeah. Honestly, I was very. Yeah. That's only funny. Thank you very much.
Shower goes.
The bonus?
Yay, speaker notes exist.
But you can look at Colorado, which is default the same as the United States or any ocean.
Even though trying to start 6 minutes earlier, you just take it off.
We're just hanging out. Yeah, can you give me 1 second?
Actually, we don't get it right now.
It's just we don't have the name for quiet, but for each of y'all. Cover your 2 sides.
Oh, this one there's
We have a lot of slower ones.
You're already the author and something. Can you call him Gavin and then we can talk about it. Y'all want them great. Listen, you're fine. It's not bad. People will be All right. Laura, you want a photo? All right, y'all.
It's down over.
Yeah, like, there we go. This one.
Like legs against the table. Also, you gotta be in like one line. You can be in 2 lines, but it shouldn't be 1 line like that.
Wait, and are these their heads walking this way?
To the tall guys. The average height of your sub team is like average height. Like, frankly, there's not a single person in your sub team is average height.
Is it average height like 5'9"?
Yeah, but we got 2 incredibly taller, and then the others are just all the same height. Sorry.
Oh, wait, let's see. No, I don't.
Alrighty.
I said last second.
I'm just gonna leave them over here. So we have a thing to do.
I also understand 9.
Wow, don't be mean, Will.
All the ones I've seen since before Adams. This one's plugged in.
So, wonderful.
There's 4. You quad.
Oh yeah, there are 4 Iranians. There are 4 values to a quaternion.
3 of them are imaginary though.
Yes, however. Alrighty.
Alrighty.
Do you want to get started? That way we don't have to stay.
Yeah, still 3 minutes. I'm talking.
And then we're muting this again.
Quaternions are most caged.
Well, yes, that is kind of that's further worse. When you have an IJ and K rather than just one
Well,
value.
imaginary, imaginary, and imaginary. If I stands for imaginary, it's something logical.
I guess, and J and K.
Imaginary, imaginary.
What is Will writing?
Quaternions, I think.
Oh.
All right, so Matt, this is how much turning they can find, okay? What? So you take it. Okay, I can't.
Oh, I have one. No.
Welcome to quaternions, I guess.
Okay, so you, Matt.
Well, you have 2 minutes.
If you're not paying attention,
Just start.
so you define a vector, right?
Yes.
And then, which is like the direction you're pointing.
I know factors.
And then you define a rotation around that vector.
Yeah.
That's what quaternions.
So like 1 quaternion. What is that?
It's orientation.
Okay.
Quaternions are not a unit.
That's not.
No. You,
What it uses components instead of 3, because the 3 components are the same.
Rotation 1.
So yeah, wait, what's the?
It's the 3, all right, so the 3, like, the direction it's pointing is this way, right?
Yeah.
Maybe let's not find out about that aspect.
mind you, there is a camera right there. That's recording this all. I mean, I guess. But if we all start getting spread to the
It's the rotation about that vector.
Immediately that we are now the last presentation of. And there's so much. Because 30, I think we're the last presentation. Since 30K composites is quit. Yes.
And the 4th number is rotation about that.
Thank you, Will, for the 90-second lecture on quaternions.
No.
We good? Wonderful. All right. I'm Nick. I'm the sub-team lead for Ground Station, and we've got a whole bunch to cover, so let's hop right into it. As sort of an overview, we have a couple of major driving requirements. So we want to be able to receive a signal and decode that signal at least 90% of the time throughout our 30K flight. 100 would be nice, but you can't always get that. So we're designed to both operate at the high data rate of the telemetry radio system we're using and to support the bandwidth of the COTS live video system that we're using. SRAD live video would be quite a subject. We need to obviously interact with the recovery and avionics bay for rocket recovery through 30K and mechanisms for the 2-stage. And then we need to also work with our flight computer for software and electronics. We need to be able to handle, things aren't always perfect. We're not going to have a perfect radio environment at the competition. So there's a whole bunch of other teams need to handle interference from them. And then overall, we want to try and compete as best we can for the best live video and the best telemetry visualization awards. Notably for us, there's a bunch of new regulations required in regards to RF this year from the DTAG and from Ezra. So these were all as of today. So mainly from the current update of the DTAG, there is a lot of restrictions in most of the bands we were using previously, including notably the 915 megahertz band where we used to do telemetry, 200 milliwatt of max power for those, and then and a bunch of other restrictions in terms of no frequency hopping and that sort of thing, which make it just easier for us to use other bands for our custom systems. APRS will still be done in the 70 centimeter band with the tele GPSs as we've done in the past, but those fall within these rules, so we're all good there. Like I said, there's no frequency hopping, and notably for those tele GPSs, there are no LiPos allowed in the flight vehicle at all. This doesn't necessarily directly impact ground stations. The tele GPSs aren't necessarily our thing, but this does limit what kind of other transmitters we can use, at least directly. And then
kind of the official Ezra Discord has been acting as sort of an in-between update between your major DTAG updates. And so sort of larger power transmitters, which are somewhat relevant to us, will require more justification as into why we need them. This is coming directly from Jim Jarvis, who is the Ezra RSO. So we know. As for knowing that our systems will actually perform up to spec, we need to do some more testing. However, the big thing we want to know is, how does our received power, as in how powerful is the signal we're getting on the ground, relate to either the packet error rate, so how many packets we're receiving but we're not actually able to decode, or how good our video will look. And then also, how does local noise, it's rather hot down at IREC. So in that case, a lot of the radio systems have issues with noise at very high temperatures. So knowing how that impacts it. We've done some basic testing with that in terms of the performance of our systems this term, or this past term and a term, but we're doing a lot more of those this term. And as of what we're going to try and get, this is an example from an IEEE paper that got published. And this is giving us the bit error rate as a function of the signal to noise ratio. So basically how powerful our received signal is above the noise floor for the LoRa modulation. This is obviously theoretical, but we would be following this. Assuming our radio modules live to spec, we'd be following this this circled line here, which is equivalent to a spreading factor, which is a LoRa thing, of about 7. In terms of the radio modules themselves, obviously we can't really use the XBs anymore because those are not allowed in the way they operate. So we're using these E-byte modules. You know, we've had some issues with the E-bytes in the past, but that's fine. LoRa modulation, it's in the 1.25 meter ham band. Data rate is a little bit lower, but the radio performance is a lot better, which means we don't need as insane of antennas, so no big dish, to be able to receive a good signal from them. A little bit higher power, but in reality, the actual power output, as we've measured, is about the same. And then these are really acting as a step towards a custom radio system in that 1.25 meter band. As in, this is allowing us to build out the antennas and that sort of infrastructure this year before spending more time next year working on those custom radios. It's also a less commonly used band, so we should have to deal with less interference. Similarly, for the analog live video, this is the ready-made RC 1.2 gigahertz transmitters. We tried to use these last year, but had some issues with wiring, which is why they didn't work. But we've been doing some testing so far this year, and they seem to work pretty well. That photo was taken at about a 1.5 mile range, so works pretty well thus far. That's not quite as far as we need to get, but it also gives you pretty high quality video. So it's also a band that gets used less often for live video. So again, less interference issues. Just sort of looking at how much gain we're going to need from our antennas. You do all the calculations out for our telemetry with what we assume to be our custom radio modules, needing about -60 dBm of received power. We would need about 14 dB of actual antenna gain for our telemetry system. Again, we don't necessarily need this with the LoRa modules this year, but with our custom radio modules, which is really what we're trying to build for, we would need about 14 dB of gain. The live video system is a little bit rougher because you get a much higher path loss due to it being a higher frequency. And so for that, we're going to need about 30 dB of gain between antennas and probably amplifiers. So I'm going to now pass it off to Finn, who's going to talk a little bit more about the antennas we're going to put on the Rocket.
Hi, I'm Finn. I've done stuff with Rocket antennas. So first of all, design goals. For telemetry, design goal is to have wide enough bandwidth to handle the fairly wide 250 kilohertz of LoRa, as well as having reliability, which you'll see why that's important in the next slides. For live video, the biggest kind of constraint on that was making it compact so it actually fits in the avionics bay, and optimizing for gain to increase video quality. As you can see, the link budget for live video is pretty tight in the previous slide. For the live video antenna, the plan is to do a spiral dipole antenna with a reflector, which is not like the phase 2 spiral dipoles previously used, but is like a little bit more compact. Should be 80 degrees, half power beam width, 5.8 dBi gain. Those parameters might be a little bit less depending on actual implementation and tuning and stuff, but the rough estimate, and is also shown here how that's actually placed in the recovery bay. 2 PCB antennas spaced roughly 1.5 inches apart, and that'll stay well within all the threaded rods and stuff inside the bay. And it also has a directional radiation pattern that should point mostly down, so we get most of that reception at the ground station. For the telemetry antenna, the plan is to do a rocket body QFH quadrifield or helix antenna, which should have 40 degree half power bandwidth, and about 4 dBi of gain. This antenna would be wrapped around the bottom airframe above the fins and below the coupler above it. And that will be connected to the recovery bay with coax that runs along the shock cord. And there'll be the feed point and tuning stuff down in the bottom part of the rocket. And the coax would have to be strain relieved and pretty well attached to both of those. Another thing about this is the feed point that is on the bottom for this antenna can be installed either before or after the antenna is actually wrapped around the bottom part of the rocket, which adds a little bit more flexibility in constructing that bottom piece without being overly constrained by the antenna. And the idea is to use thin copper, which has been demonstrated by Nick in some prototype helix antenna designs, wrapped around that too again. Then also, since this antenna is wrapped around the bottom of the airframe, it's fairly thin copper. Its only real protection from the environment is like paint, and it's also attached with coax running along the shock cord. There are more failure modes than if you just had an antenna that was in the avionics bay. So the plan is to also have a small, short, not excellent antenna, but a backup in the recovery bay that is just a monopole, electrically lengthened, so it just works. But another thing is that that's really not a great option, and especially with like future custom radio stuff, probably not really viable.
I'm Barrett, and I'll be going over the payload antenna. So once again, we're operating at 222 to 225 megahertz. We're using the e-byte module. And the primary design consideration for the payload antenna was for it to be small enough so that it could be stowed during flight and then we'll deploy it upon landing. We also want a low wind area since the rover is relatively small and we don't want it blowing over. And due to the payload being closer to the ground station, we don't need as high of a gain as compared to the rocket transmitter. So for our antenna types, we considered monopole, dipole, and helical antennas. The concerns over the monopole and the dipole were that they would be too tall to fit into the airframe, while the helical antenna would have trouble meeting the requirements of a low wind factor. So ultimately, we decided on a variation of the monopole, which is a loaded monopole, and it uses a coil, which allows it to be shorter while still being efficient and matched to our desired frequency. And this can be easily lowered and raised with a servo. And this is convenient since payload already has electromechanical systems in place. And it's going to be an omnidirectional pattern with about 2 dBi of gain.
Hello, everybody. Most of you probably already know me and what I've done. But if not, I'm Ben Peters, and I was the lead for this team last year. So for receiver antennas, there's a number of different options that we've looked at. And as you move to the right on the slide, the performance of them does get higher in terms of gain, but so does the complexity, weight, and associated cost with them. So essentially, we want to figure out what is the farthest left on that slide we can be. What is the minimum performance where we can still maintain that link without making it super expensive. For both cases, we believe that the best option is going to be a Yagi Buddha antenna. This is slightly different than last year, as last year we ended up building the big reflector antenna. But when taking the entire antenna system into consideration, both the receiver and transmitter antennas, we think we can get away with the Yagi this year. First off, to talk about the telemetry, the one I've currently got designed does have a fairly large physical size. It's about 1.8 meters long and half meter wide. However, since it's not a massive dish as last year, it is significantly lighter, much less wind loading, and much easier to actuate. The standing wave ratio is under 1.5 for the entire bandwidth that our LoRa modules support, and it has a peak gain of 9.6 decibels. While that's a little bit lower than the 14 decibels we said we would need, when taking into consideration that we are also accounting for the transmitter antenna gain, which was about 6 decibels, that gives us the 14 we need with a little bit to spare. It has a 60-degree half-power beam width, meaning we don't have to be like 100% right on target to still be able to receive it. There can be a little bit of error in the tracking system. Now the more difficult one, this is the live video, which we've also gone with the Yagi antenna. And you'll notice that this one, while it is a 15.2 decibel peak gain, that is a lot less than the 30 decibels that we would need to maintain the link. And we're hoping to get the rest of the gain from an amplifier on the receiver end, as well as from the transmitter antenna, though the transmitter antenna will only be giving us a couple decibels. It has a smaller beam width because it has to be more directional to get a higher signal, which means that this one needs to be a little bit more accurate and will likely be the driving factor constraining tracker requirements. It's a tiny bit smaller at only 1.4 meters long and significantly thinner. The VSWR is slightly better for the main channel we plan on using, though slightly worse for a backup channel, though that will be improved over time. This is just a first pass design. Speaking of tracking, I'm now going to hand it over to some other members of the team to talk about the tracker setup.
Hello, my name is Connor Nixon.
And I'm Jacob.
And this is tracking. So this is last year's tracker. It was massive, it weighed a ton, and it took upwards of 30 minutes to fully assemble, and also had several sensor reading, acceleration, and positioning issues. These are the graphs for the angular velocity, angular acceleration of the elevation of the tracker half a mile away from the launch site for the 30K flight. The maximum angular velocity was determined to be 10.7 degrees per second, and the maximum angular acceleration was determined to be 3.4 degrees per second squared. Locomotion goals. So last year's tracker had issues accelerating and staying at speed. So this tracker will have high factors of safety to ensure the rocket can be fully tracked during the rocket can be tracked during its full time of flight. So for elevation, our factor of safety should be roughly around 3. Our target angular velocity should be 3 degrees per second, and our target angular acceleration will be 9 degrees per second squared. For accuracy, we want a factor of safety roughly around 4, and we want to maintain less than 2 degrees input angles, which is based off the beam width of the Yagi antennas. Construction goals. So we want the entire tracking setup to weigh less than 80 pounds, including the antennas. We want to be buildable in less than 5 minutes with 2 to 3 people, and we want to be very portable and can fit into the trunk of a sedan.
Okay. So for our design inspiration, we took concepts from last year's tracker and an additional concept to Rocket Tracker that's non-HPRC related. Some of these features include a significantly better center of mass positioning, especially regarding the center of mass and center rotation of the antennas. We'll be able to hold 2 full Yagi antennas on either side of the elevation shaft, and we'll be able to use a foldable tripod to save significant weight and size. It's a bit to unpack here, so I'll be going over the key features in our design. So for our concept on the tracker's elevation axis, most of the design choices were made to solve major issues with last year's tracker. So we'll be using better sensor positioning and implementation to ensure that there's no interference with positioning sensor data. There will be a direct gear reduction to remove the need for the planetary gearbox, which was used last year and was responsible for a large amount of weight. Additionally, latching mechanisms will be used on the Yagi antennas to ensure that it can be attached and detached very quickly. And a camera can be mounted to the shaft so that we can track the rocket and provide a much better live accurate video feed than what can be done by hand. For our azimuth axis, we'll be using an internal gear reduction to keep the assembly much more compact. And in addition, we'll be using a closed loop stepper motor and a Hall effect sensor for absolute positioning. For our tripod and electronics, a plate will be holding all our components, which can be easily and quickly clamped to the tripod. This plate can be easily expanded at any times if any new components are needed. And it adds space for physical buttons or switches if we want to change anything in real time. Some of the key design features that we'll be having is there'll be multiple quick attach and release mechanisms, which will shorten our assembly time from 35 to 45 minutes all the way down to 5. Handles will be added to each subassembly, which will make it extremely easy to transport. There'll be much more reliable, accurate encoder data, which will allow better control of the system, and we'll be using a more advanced control algorithm, which will be able to consider multiple variables such as wind disturbances, the current state of the tracker, and acceleration and velocity. And it goes to live video.
Hi, I'm Devin, and I'm going to be talking briefly about the camera part of the live video. We've decided to use an off-the-shelf camera, the RunCam Split 4v2, since it has a separated sensor and the rest of the electronics, allowing for a very small package that actually goes on the outside of the rocket, and it can record or it can transmit analog video and record digital video simultaneously, so we'll have that lower quality transmission as the rocket launches and much better quality once it's hopefully recovered. And then it also has a nice wide view angle of 140 degrees and only weighs about 10.2 grams. so keeping everything nice and light. Then for the camera angle, the goal would be to capture both, look down a bit to both capture the rocket and the surrounding environment. So we're looking at a camera angle of 45 degrees, which would protrude approximately 1 centimeter from the rocket body, but unfortunately, finding accurate dimensions was a little tricky, so we'll have to see once we actually obtain the camera. And pictured there is what roughly it might look like for the view from the camera. So now I'm going to leave it to my teammates to talk about direction finding.
So for direction finding, we have the rocket in the sky and a directional antenna, and we need to know where to aim that antenna. So to find where the rocket is in the sky, we're going to use correlative interferometry. This is the same general architecture, same system as last year. It's using the phase offsets on 5 different antennas to find which direction the incoming telemetry or incoming radio wave is coming from. With this system, we can get about 1 degree of accuracy in theory. And last year, we designed the large Luna system right there. And it used direct phase comparison at RF. So at the 145 megahertz signal. And we had improper filtering because I didn't make the design right. So the LNAs didn't work because they were amplifying basically the entire RF spectrum. So this year, I'm doing a new architecture. So we're now tracking the 1.2 gigahertz live video signal, which will make the whole system much smaller as we're doing 1.2 gigahertz and not 145 megahertz. We're going to use a super heterodyne RF front end. So instead of comparing phases at RF, we're down converting it to a much lower frequency that we can then directly sample with a microcontroller. We're going to use this LNA from Corvo, which has really high gain and low noise factor. So we should be able to still read the signal even when it's like really close to the noise floor. And then Mixer will also get extra gain from that. In total, we'll get 29.5 decibels of gain. And then local oscillator to down convert. And finally, ground setup.
Wonderful. So last year at IREC and in the past, we've had a lot of issues with there being a lot of stuff for ground station, to put it in the most simple case. You've got various receivers for telemetry and for APRS and for live video, and you need to be able to communicate with people with PAD. And it just generally becomes a mess. Like at IREC, there was a whole 4x8 foot table that we used basically the entire space of because there was just so much going on. It was all a mess of cables. It was very hard to troubleshoot and figure out what was going wrong or verify that things were actually working correctly. So to solve one of the issues we had last year, where we couldn't hear people at the pad very well when we were at the ground station, we're going to be using a mast to lift an antenna up high. It's not going to be quite that big, but that's a good example of a photo. We're looking at about 10 feet of vertical height on that mast. That's about 30, if I remember correctly, 15 to 30, somewhere in there. And then we'll be using a larger 20-watt radio at the ground station so that at the very least the people with pad in here can hear us better, and it's also generally more sensitive and be able to hear weaker signals than your little handheld radio, partially because it's got a much larger antenna. One of the other things we're going to do is, that did not quite work. There we go. We're going to use a Pelican case to store most of our radio hardware. That way it becomes a lot easier. All we have to do is open up this Pelican case. We've got our antenna connectors here on the right side. Goes through all of our various systems for telemetry and APRS and all that. And then we've got a single USB connection or two or whatever, a couple of small connectors to go to the laptop. And it's all contained into this one roughly laptop-sized Pelican case rather than being spread out across that entire giant table. Makes our life a lot easier, makes it a lot quicker to set up. That way we're sitting there kind of in line with our tracker setup. It's about 5 minutes to set up rather than 30, trying to make sure everything gets plugged in correctly. And then for our software, this is a little bit earlier compared to a lot of the hardware work and the hardware planning we've been doing for this term, but we're going to be using Tori, which is kind of like Electron, if you've heard of that, but it's designed to be a little bit more lightweight. That way we don't have as much delay or as much lag in that whole system. So this can use either C++ or Rust as a backend. We're currently going to be using C++, And then it can either use JavaScript or TypeScript as a front end. We're currently going to use TypeScript because that gives you statically typed, allows us to actually specify that, yes, this is an integer, or this is a float, or this is a string, rather than just kind of being like, oh, with JavaScript. That allows us to use most like modern web development front ends. In this case, we're going to be using React just because it's a very common front end. A lot of people know how to use this as compared to some of the more niche options, which might perform a little bit better. But given it's just displaying the information, it doesn't need to be as performant as compared to taking all the data in. Again, currently in early stages, we've got some basic things building, but this will be one of the bigger focuses this next term and going forward. As for the whole infrastructure of the program, we're going to have this middleware part here, which is almost acting as a database in a way that handles our data export out to CSV, so we can have people be able to use the data afterwards. And then we can have various different modules, either on the back end or the front end, that plug in a way. That way we can develop each of these pieces of code in an isolated way, rather than having a giant singular backend module that handles the data storage and taking data in from all the various sources. That just becomes a pain to maintain. So we can have, our radio interface module and the module that interfaces with the tracker and the live video systems that all feeds into that central database. And then we can have our individual front end modules for displaying to the live stream, displaying to ourselves, and then, controlling, okay, I want to turn on the live video system. Okay, I want to connect to this radio module or this serial port or that sort of thing. Makes it a lot easier to develop and sort of keep this as a maintained thing long term, rather than having one giant block of code that's very specific to this year's hardware or this year's requirements. And that is finally all we have. Quite a lot of slides, I know, but if you have any questions, please go ahead and get us started now. Geez, all right. There we go. I figured.
So I have some concerns about the whole coax cable along the drone shock cord thing. Is that something that you have reference to other teams doing and how they've implemented such a thing? And can you be more specific about the strain relief plan on that?
Okay. First of all, I completely understand your concerns of coax on a shock cord. When that idea was first I was made aware of that idea. I also thought it was really kind of a bad idea off the bat.
It's not a great solution.
Yeah. So a couple of different things for strain relief. So first of all, the coax will be a fairly thin coax that's relatively flexible to try and avoid kinks and stuff like that. It'll also be tied to the shock cord at multiple places on its journey, and the shock cord will be wrapped in a way that to optimize its exit when the rocket separates. Another idea that we're considering is putting the coax inside of a piece of tubular like Kevlar or nylon or something that is really strain resistant, and then tying that at both ends in addition to the shock cord to provide a direct strain relief for the coax that would take any loading that would be applied to the coax in case there was ever a scenario where that did happen. And also having just good attachment for the coax on either end, not having just RF connectors kind of mate the coax to the avionics bay and to the bottom of the rocket, having the coax attached there, having all the tuning and components there, managing all the wires nicely so it stays out of the way of the eye bolt on top of the motor, stuff like that.
Can I add a little bit to that? There's not a lot of prior art in terms of running coax down shock cords, but there is a lot of prior art in terms of running igniter wires down shock cords. It's a little bit of a different thing. Coax is a little bit more persnickety than igniter wire, but it's not that this is a brand new thing, running wires down a shock cord. Yeah. Yes.
And as one follow-up, as kind of an alternative backup, have you considered using some kind of wireless that's local to the rocket to transmit between where you're doing the computing and where your antenna is?
The problem with doing that is that would then mean that we would need to put an extra microcontroller, that local radio module, as well as our main radio module, and a whole bunch of batteries in that lower section, which is not a great choice just in general. It adds a lot of complexity to that system, and it would be that's an extra thing to power on, an extra thing to make sure that's working, which is a lot of complexity to add for that sort of thing.
that particular thing, as somebody who spends some time with recovery stuff, the first thing I would say is, how long are you planning to make the cord relative to the shock cord? Because assuming that the recovery system works like every recovery system I've ever seen, it's gonna spin a lot, and having something on the shock cord doesn't matter that's attached, unless you have it attached somewhere where it's like a loop around the shock cord, so it spins inside of the attachment point. It's gonna end up twisting around the shock cord and you're gonna end up breaking it because there's too much line on it, especially since they swivels. But actually,
well, so we're talking, that's one answer, but it's so much longer and if we mounted below that.
That's what I was trying to be sure.
It's gonna be really, like, the shock would have to snap and start twisting the glass.
Okay.
Yeah, and just so you know, they have been working with recovery. Just so you know.
This was like the first thing, our very first integration meeting. It's like, okay, I realize this sucks, however.
Okay, I also just wanted to question, make sure that there are going to be some sort of tests done like about making sure that that system works. I don't know, like maybe something from a hexacopter, like I don't know, some sort of testing this to make sure that the system that we have at present plan works.
Yeah.
Especially because the rocket recovery
Matters a whole lot more, yes.
historically not necessarily been the greatest. And I want to make sure that nothing affects the system and also.
Yeah, that's obviously rocket recovery is a little bit more important than running our little antenna because you kind of want the rocket to come down in one piece. As much testing as we can do, that'd be great. I know there's things in the past where we've done like someone goes running across the field and that pulls it out and plays with that. We could look at doing something, something like that where we play around with seeing what happens when we twist it, or possibly bringing it up in the hexacopter and doing a drop test. Whatever is available as options. Ooh, yeah. I like that idea a lot, even if it's not actually connected to anything. Yeah. Yeah. Yes. Yes, we plan to do a lot more testing on basically every system as compared to last year, where like the live video was hardly tested in D term, which is not really the time to be doing testing. So we're trying to make sure that everything is reliable as we can be. And I can definitely talk with Matt more about testing that at the launch.
Well, there's like an app.
Yes.
Kind of tangential to that. So for the backup antenna, how do you switch between the antennas? And when can you do that?
We discussed it.
There's a couple of different options, either that this becomes a thing of there's kind of two different options. One is that we add a passive splitter in there that makes it so that that's an automatic switchover where it's feeding that signal to both antennas. You do get about a 3 dB loss in that, or if you get a more expensive splitter, you can get less loss, but it's not that big of a deal. Or we could physically have it where if we've noticed very obvious damage to the antenna, depending on how durable it ends up being, we can pop open like the top bulkhead of the recovery bay and just switch over to switch to a different connector. No, if we have that passive splitter in there, nothing would need to happen to fail over, which is the ideal case. It's just that's more mass, that's more space, and then that's also not optimal from a link point of view, but that's okay.
I never really know.
Yeah.
The passive splitter basically kept both are transmitting.
Yes.
So is there any, and I said the 3 dB loss in terms of like the actual splitter, is there any sort of interference that you're gonna get?
Not really. It's not significant enough to worry about. Like, yeah, but. Yes.
I think that would should do something like the glass cable, but next time.
That sounds like a good plan there.
I think that's fine. How big are they?
There's a couple of different options. There's the one we used on the avionics bay last year. That one's now obviously not usable, but we can get another one. Yeah. Awesome. That's adding extra complexity, and there wouldn't really be a good way for us to like on the, because if that gets driven off the Mars board, there wouldn't really be a good way for us to know when we've lost like that antenna working. Yeah, or if that antenna fails, then because it's largely a one-way link, it's very difficult for us to actually know that that antenna has failed.
Well, my thought was like, if you have a link from the ground station and you're sending a message, like you send a packet from the ground station every second, it's 10 seconds, so you will last receive. But maybe that's just too much.
That seems like more especially with the LoRa modules this year, we can tolerate a 3 dB loss. Obviously part of the hope is that we can get these body wrapped antennas to be reliable and strong and effective. Then we can use them in the future with custom modules where we can't really tolerate as much of that loss, but
maybe half of the time.
Yeah, we can take the loss this year. We can just use the passive splitter. Sounds good. Awesome.
Out of time, but the last one that people wanted to ask.
Yeah, just in case anyone didn't hear. So, Jim requested to move the box to tomorrow. So I don't know if you guys want to. You know what? Box actually.
Yeah, we're gonna keep going.
Last.
Yeah, keep going.
Okay. And we deal, I think we talked about, but I don't remember the answer. Can we be able to record and stream a live video at the same time, in the same camera?
Oh, yeah.
Yes. That's the specific camera, and there's some stuff on the antenna earlier, but
yeah, that
transmitting.
That camera very specifically supports recording that 2.7K at 60 to a local SD card on that board, but then also supports the output we need to feed into our transmitter, which is why we selected that camera.
We don't know how that's controlled.
It's on the website. I forget off the top of my head, but it's not significant as compared to the transmitter's current requirements.
And it'll be remote.
Yes.
Well, has the big one been done or the?
Sorry? Not at the moment. This is something we plan on working more on in midterm. We've just focused a lot of the past term or so on getting a lot of the hardware in place because as compared to last year where it was a lot of software work and very little hardware, which caused a lot of the issues this past year. I think Colette has a question.
Rewriting of code. Just me, which is in your platform.
A lot of the backends, it ends up being almost a complete rewrite, unfortunately, just because we're moving away from Qt, which provided a lot of like the serial interfacing and that sort of stuff, as well as the UI elements in the past. The reason we're doing this specifically is we're trying to move to this infrastructure, which will support not having to rewrite the entire system and being able to sort of switch out components as required. So if the team decides in the future to move to Rust, we can do that for the back end, or we can use, different JavaScript or different front end platforms, I guess is the word, for doing UI development without having to switch over every single piece of code in the future. Which I know we've said I know this has been a repeated thing with ground station leads of switching the software to support this exact same thing, but I think being able to do this sort of separation will help a lot more with that.
I was gonna say, I know I said the same thing last year. This is like an absolute. Because what the plan is to use is like actually for this.
Yeah. Ooh, there we go.
It takes a lot of GPU.
It also doesn't like my 40 megabit image.
Yeah, nailed it.
There we go.
Cool. So this is a question. Also just the composite stuff. For this, maybe it was just. Yeah, okay. She said that you have this 60-degree half power beam. How extractor box just said really close. It's like this.
How is one like this actually just like
better? Do you want me to?
Oops. Sorry. So half power beam width is actually just kind of a function of gain. There's a few other things that affect it, but essentially a really high gain antenna is going to have a really tight beam width versus a lower gain antenna is going to have less of a tight beam width. So since we only need 10 decibels, it just comes out to be like a 60-degree half power beam width. We could concentrate it more and make that a smaller beam width in exchange for better performance, but that would drive up the size and cost. So it's a trade-off, and I think this is kind of the best solution we have right now, because in the event of a tracker failure, it's fairly easy to point by hand since there's so much margin for error. Oh, with the camera? Well, I think it's a,
The camera's at a weird angle, right now your head's not.
does it go all the way to the top?
It goes all the way above your head.
Okay.
Wonderful.
So don't go any further.
I'm done with my question. Wait,
Back to you. Oh, also, sorry. They came up with an idea for the coax cable splitter problem, so that's what they're talking about.
Wonderful. I will talk with them later and we'll communicate separately.
That's the question, but just like, it's a reminder. Because, the package is going to be very optimistic. I would definitely create calls of tests and to stress test your software application. With like the worst case scenario possible of what you think will happen. Because I know expert producing different weights and stuff. And you can run into issues if it's written poorly. So yeah, just be aware of that.
I heard, I think most of that. By any chance, could you type that up and send me a Slack message or send that in the ground station channel just so I can keep that on my head rather than having to memorize it? Thank you. Go for it.
Does the pad crew need different equipment for the radio receiver, or like the big mass thing is like able to use regular radio?
Sorry.
For the big mass for the radius for while we're at the pad, to the pad crew, do they need anything else or no? We can just do the regular radio.
Yes, that's the goal, is that because we're creating such a larger setup on the ground station, it makes it so that there's less requirements on y'all's end. There's less requirement on y'all's end for getting reliable communication.
You don't have a problem with that?
There were also teams with like 20 or 30 foot tall masts last year, so they didn't have some issues.
Probably just confirming it this year.
We will, but
I,
yes,
Okay.
because we also can confirm similarly with the tracking system because it's of similar size when deployed, but because of how the fundamental construction of the Yagis, it allows us to pack that down much smaller. So we're not having to fit a 2 meter long thing in the car. We're able to pack that down into a much smaller size. Yes, that's my plan.
slide 1.2.
We had a lot to cover.
It was really impressive.
How did you arrive at the -60 dBm?
I've been looking, this was partially, I was doing this summer also. I've been looking at a lot of the different sort of, because we're not building a completely custom radio module here. We're still going to be buying like a chip that's fundamentally doing most of the RF stuff. And this is a like worst case on what most of those chips would be able to take in terms of like, we need a significant, like a lot of those need a pretty significant signal to noise ratio and their absolute sensitivity. So at the absolute bare minimum, they could receive a packet is like -80, -90, somewhere in there. Most of them need like a 20 to 30 dB signal to noise ratio. So this gives us a good margin with those modules, which are a lot less sensitive than the local LoRa modules we're using this year.
And slide 126. Fire with the reflector. Orientation, like, are you sure that the antenna will be pointed down? Like, I know during ascent, the antenna will be pointed down. But like
for video over telemetry or something.
For live
steps away.
Yeah.
On the way down, especially under 2 parachutes, things might like shake a little bit. Are we concerned about that?
Yeah, it's a valid concern. We've basically optimized the live video antenna just to get as much bandwidth, not as much bandwidth, as much gain as we possibly could for when the rocket's descending, so we make sure we have high quality video. To be honest, I haven't done any really looking into getting that for the kind of side as the rocket might be falling down. If that's a serious requirement that we want to have video when the rocket's coming down in reasonable quality, we can look into doing something more oriented towards that, but mainly we've just been thinking it'd be good to get video in the rocket.
I believe also when we've been in our integration meetings with recovery, even either under drogue or under May, or that section for the recovery tube is still vertical. And as you can see here, this is our main beam pointing downwards, but there's also a secondary beam of a little bit less power pointing upwards, so that regardless of which orientation that is, especially under descent, where we're going to be coming down not quite as, we're going to be a little bit closer to ground, especially in the main. We shouldn't have as much of an issue with that.
So, it will be upside down.
Okay, that's,
But that's like not that bad.
I also,
Even
yeah,
upside down, it's not that bad.
yeah, it's not optimal, but we can work with that.
it will be upside down for the drone. Also, usually after the drone, the pocket spins out a little bit.
Okay.
But also that being said, but necessarily video is gonna be the greatest no matter what, because the rocket is gonna be doing some funky things.
Well,
Yeah, that's part of our requirement is being able to get it through 90% of the whole flight, but
it's, you know, my video last year.
that was 2 years ago. 2 years ago, they only got pad footage. This past year, they only got up to apogee, I believe.
Yeah.
But
Yeah, and on slide 127, I'm just curious, which direction is the gain on this? And like what orientation, like in the rocket, is it this orientation or is it?
Yeah, sorry. So this image is probably not the clearest. The bottom where there's the feed point where the spirals are actually connected is at the top by where the I-ring will be. There'll be a PCB there, there'll limit distribution, but there will be a hole in the middle first to let the eye bolt through and stuff like that. And that gain is specified out the top of that image, which is out the bottom of the rocket. Also, I thought there was a radiation pattern in here, but I think I added it like before this presentation got copied, added it after, but there is also still significant radiation on the other side. I'm forgetting whether it was like almost equal or it was significantly less, but I think it's pretty relatively equal.
it's also specifically for this year. Obviously, we want to try and design for the systems in the future, but for this year, that will be fine. The Valora, we have so much in our link budget for these specific these like stepping stone modules we're using that some of these non-idealities will be okay. I think, Owen, you had a question?
Yes. What is your plan or your strategies for not having the antenna tracker tip over?
If y'all want to talk about this more, but I can also talk about some of that.
We've been doing some research into finding trackers that have a very wide base. Possibly even the consideration of having multiple tripods, spaced very far apart. Excuse me, spaced very far apart, just so that there's no chance of tipping at all. There's really no wind impact on the Yagi antennas in comparison to the dish. So we're anticipating that wind won't be as big of an issue as last year.
That CAD model also does not have the legs of the tripod fully extended, I will say that much. So you end up with a wider base as compared to what you see in the photo. That's also an option if necessary. It just becomes kind of an issue trying to get guy wires on there because of the very long Yagis, but we can run guy wired, which means that you have to run them fairly low, which limits their effectiveness.
Let's focus on just.
Yeah.
I mean, it won't be so windy that the one.
Yeah.
It did get, like, there was a tornado at the launch.
Yes.
Here, so like,
Another option is we can look at like weighing down the legs with like sandbags or something like that.
yeah, that would be
For the tracker, I assume battery requirements are gonna be less because there's less work required. Maybe.
We'll be using.
Maybe there isn't less work.
There, for sure, there's definitely less torque required. Yeah, the antenna is a lot lighter. The center of mass will be positioned a lot better as well, so there won't be as much torque needed. The motor is a lot smaller as well, I believe, and we'll only be using one instead of two. I'd imagine that would lower the.
I mean, we already have
We'll be able to reuse those lipos, yes.
Yeah.
Which we're also allowed to have lipos on the ground. It's just not any in the rocket.
Yeah. And then kind of on the same note, we were pretty worried about heat last year. Our IMU pointing stick overheated. We didn't have the tracker overheating, but it's possible that's because it was like literally an umbrella. The dish is heating a concern in the sun if there's not much light.
I think I can. I know as a memory from last year, the elevation motors got rather hot, but that was because they were being driven at basically full stall the entire time because there was such a low factor of safety on the access control. In this case, we have a much higher factor of safety. Last year, we were kind of limited on our factor of safety by the size and therefore the cost of reasonable cost of motors. We can't exactly go spending it $500 to $1,000 on one motor, so we were kind of limited there in terms of our factor of safety. This year, it's a much smaller, much lighter system, so that should be less of an issue. We also didn't see major issues with performance degradation from like the motors overheating as compared to like the performance issue. Performance issues I saw in Worcester and D-term were rather similar to what we saw in Texas. So that's not a major concern there.
Sorry, with this slide, are these numbers from last year or this?
So this was taken from, bottom left corner.
Okay.
Um,
That was my question. I was like, because the 30 is going much faster.
Yes, we made sure that we use those.
One more question. Also, by the way, like we're over time, so you guys like don't want to answer questions.
We can stop it.
But we can.
Yeah, if any of y'all need to go for it,
I've got time.
Like I will keep asking questions, but like.
Yeah.
If I ask a question, so I'm for the tracker, how many of the components can be reused from the previous year? And like, do you have any idea of like what the cost might be, considering we could hopefully reuse it?
I haven't made a bill of materials yet, but as I'm designing some concepts, I'm considering, actually, I'm designing it around parts that we've used last year, such as same shaft material, some same support beams, aluminum channels. Yep. Wood, I imagine, would not be too big of a concern in cost, but the biggest cost would probably be new stepper motors and controllers, because I think we'll be changing those.
Specifically to ones that support the closed-loop feature within themselves. That way we're not having to rely like quite so much on us having to use custom code to control those at reasonable rates using built-in closed-loop systems from the manufacturers, which are a little bit better tested. As a point of note, also that HPRC tracker costs about $250 all in. So it's a little bit smaller scale, but it excluding filament also, but it's not a crazy price. No, the one on the right was about 250. It's the big photos.